Okay. Hi, everyone. Welcome back to the third day of AKBC, the last day of the main conference. We have a full day ahead of us and also 2 days of exciting workshops. But now you're here in the outstanding paper session. So welcome. So as Danchi mentioned in the opening remarks, we had 71 papers that were submitted to AKBC this year, and 33 of those papers were accepted. We had the archival category, and 29 papers are archival and were eligible for an outstanding paper award. The program chairs, in consultation, close consultation with the area chairs, created a short list, and an outstanding paper committee eventually selected 3 outstanding papers to receive this year's award. So without further ado, the outstanding papers are in random order, but this will also be the order of presentation in this session. Behavioral testing of knowledge graph embedding models for link prediction by Wiem Ben Rim, Carolyn Lawrence, Kirill Gashtiovsky, Matthias Nippert, and Naoaki Okazaki. Psycho, hierarchical cross-document co-reference for scientific concepts by Arya Katan, Sophie Johnson, Daniel Weld, Ido Dagan, Yves Beltagi, Doug Downey, and Tom Hope. And last, manifold alignment across geometric spaces for knowledge-based representation learning by Huiru Xiao and Yangqiu Song. So the format of the session, we will hear 10-minute talks from the authors of these papers, and we will have 3 minutes time for questions. And at the end of this day, we will have our usual poster session. You're welcome to talk to the authors of the outstanding papers in the poster session as well. So warm congratulations from all of us here at AKBC. And we can now start with our first speaker, who is Wiem. So. Hopefully things will work. Again, this is Wiem with behavioral testing of knowledge graph embedding models for link prediction.
Wiem, you're muted and your screen is just black.
Now we can hear you.
Okay. Sorry. Can you see my screen?
Yeah, it looks good now.
Okay, sorry about that. Okay, so hello everyone. My name is Wiem Ben Riem. Today I'll introduce a paper titled Behavioral Testing of Knowledge Graph Embedding Models, which I worked on together with Carolyn Lawrence, Kirill Gashtiovsky, Matthias Nippert, and Naoki Okazaki. Suppose that you have a knowledge graph and you want to predict a new link, like where Tokyo Tower is located. One way to do this is by using knowledge graph embeddings, which represent a method of encoding knowledge graphs. They can tell us how likely it is that Tokyo Tower is located in Japan. When we test models on the task of link prediction, they take a test set of triples and make predictions for each triple, then compute some average metrics that basically allow us to compare which model is better on some dataset. What is lacking in this evaluation method is that these numbers don't tell us enough information about what the model is good at or bad at. And we can answer these questions by using behavioral testing, which is a software testing methodology concerned with testing different capabilities of a system as if it were a black box. You give the input and you wait for the output without needing to analyze the inner workings of a system. Let's look at a simple example. Suppose that you have a software that can calculate the square root of numbers. If you give it an emoji character or a string, the app might crash. One way to address this is to test for these cases and to provide solutions for them, such as to notify the user of the error instead of making some incorrect calculation. If we go back to knowledge graph embeddings, then the idea is to apply the same idea of behavioral testing for KGE models. Overall, the goal of the project is to more systematically test KGE models to better understand what they learn. This has many benefits. For example, It will allow us to compare under which situation which model works better. It will allow us to uncover issues with datasets. And since many applications are powered by KGEs, like search engines and recommender systems, this will allow us to showcase the capabilities of the models to end users, fostering trust. As for our proposed approach, we develop and run a set of behavioral tests on different models to evaluate them on certain capabilities through a testing pipeline. First, we create test sets that target some important capabilities of KGE models. Now I'll explain what a capability is. A capability is a property that a system possesses that describes tasks the system can carry. The calculator software I talked about earlier has the capability of calculating the square root of positive integers. Next, we will evaluate our trained models on the test sets that we created. Then, we will conduct an analysis of the results in the form of a detailed report and hope to get insights as to which models are good or bad at learning certain capabilities. We find many interesting capabilities to target, but two of them stand out: relation symmetry and entity hierarchy. We chose these mainly because there have been KGEs developed specifically to target them. This gives us a chance to confirm if a model is good at these capabilities and was evaluated correctly, or we can expose weaknesses instead, which will allow us to improve it. Now I'll explain the first capability, symmetric relations. Symmetric relations are relations that are equivalent in both directions. One common example to remember is spouse. For instance, Barack Obama is the spouse of Michelle Obama. So we don't need to mention that Barack is the spouse of Michelle because it's directly clear from the relation that the reverse is true. From this capability, we want to figure out one main thing. Do models understand symmetry at all? To answer this, we designed 4 different tests ordered in increasing difficulty. All models in principle can understand, all models in principle can learn that a relation type is symmetric. Now I'll explain the tests we designed. The first one should be the easiest. It checks how well the model learns the training data and should be a baseline for the other tests. So if we have a triple, Steve is friends with Steven, we can take this triple from training and test on it as it is. The second test is a bit harder. If we have a triple, Michael is the peer of Paul, then we can try to check if the model realizes that this is a symmetric relation by testing on the opposite direction. So we check if the model knows that Paul is therefore the peer of Michael Jackson as well. The third test is a bit more challenging. So in the training this time, these entities, Idaho and Utah, don't occur together. Maybe we know that Idaho is in the US and that Utah is known for its beautiful mountains. So Utah and Idaho will be known to the model, but the model doesn't know explicitly how they are connected. So we go test on whether Utah adjoins Idaho and whether Idaho adjoins Utah, which we extract directly from the test set. We also have other tests that you can find in the paper. Now let's look at some results. On the leftmost side of the figure, we show the results on the original test set. We notice that our results on the original test set do not reflect the symmetric capabilities of models. We highlight one result, which is that of the complex model, where we find that it performs relatively badly on the original test set. Actually, it's second to last. But on the symmetry tests, it does pretty well. It's good at memorizing symmetric relations in test 1. It's good at recognizing them in test 2. And it's even the best at detecting them on completely unseen instances in test 3. We also find another interesting result. These behavioral tests expose previously unclear differences between models. For the models in red and brown, we can see near identical performance on the original test, but it's clear which model is better at symmetry. Now that we're done with relation symmetry, we'll move on to the second capability, which is entity hierarchy. Entities in a knowledge graph are usually attributed to an entity type. For example, the entity Einstein has the type scientist. These types get more and more general the more you go up the hierarchy. So a scientist is a person, is an agent, is a thing. First, we set up our tests by dividing testing triples by the tail entity type and its level in the hierarchy. In the top level, Bush Jr. is a person, which is a type that happens to belong to level 2. So we place this triple in the test set of level 2. In the bottom triple, New Jersey is a state, which happens to belong to level 3. So we place the triple in the test set, and the corresponding test set. This way, we'll have 4 different test sets that cover different levels of the entity hierarchy. So in this capability, we want to figure out, do models respect type hierarchy? To do this, we designed 2 different tests. I'll only present the first one. In this, we just evaluate our models on the test sets we previously created, which are separated by the entity hierarchy levels. We want to know if KGE models understand and respect entity types and type hierarchy. In other words, if we ask a model, where is the death place of Albert Einstein, does the model know that the answer should be a location, whether it's a general location like any place or something more specific like a state or a city? As for our results, we find that models do indeed have an implicit understanding of entity types in various levels. We find that the performance of all models drops significantly in some levels. For instance, for level 2, it seems to be the most difficult. Upon further inspection, we found that level 2 contains the most challenging relations, which span over a large portion of the entities. As for level 4, where models also struggled, we found that it contains relatively rare relations in the training set, which makes it more difficult for the models. To summarize, with our framework, you can find out what are models good at and where they fail systematically. We also explored 2 capabilities, and we hope to collaborate with others and to add more capabilities, models, and datasets to our open source code. So feel free to contribute. Thank you for your time. I'm happy to answer any questions.
Thank you for this great talk. By the way, maybe you can turn on your video camera, perhaps, or maybe that's not possible.
Can you turn it on for me? I can't.
You have like a stop cam or a start cam at the bottom of the screen.
Yeah, because I have to leave the. Okay.
Okay, great. So we have 2 questions, and if you want to add more while we are speaking, feel free. So first question, this seems to share a similarity to the checklist paper by Ribeiro et al., Beyond Accuracy. Could you comment on the similarity or differences of the design principles when coming up with these tests?
Yeah, of course. So that was actually our inspiration. Checklist was made for NLP models, and it exposed weaknesses within models like BERT or Roberta. But the way they tackled it, like for NLP, it's a bit different. Like if you're, they had different tests where if you change things in the data set, the prediction changes. Like if you're talking about sentiment, if you flip a word or if you change a word, the sentiment flips. It becomes negative or positive. If a tweet, for example. So this was a good flight or this was a bad flight, have totally different meanings based on the word that you changed. But we couldn't do that for knowledge graph embedding models. So the difference is that we had to come up with a different way to test it, and hence targeting like different relation types or different entity types rather than how the checklist did it. But yeah, that's a good question.
Thank you. The next question, and I will expand a bit. So the question is, did you consider composition? Like if A has one relation with B and B has some relation with C, then A must have some third relation with C. And maybe in general, like, are there any other expansions that you tried in terms of tests that would be interesting to talk about?
Yeah, in the paper we mentioned a bunch of different capabilities that we wanted to work on, including like adversarial attacks and other types of relations that we wanted to work on, also composition. But because of the timing of the project, we had to kind of cut it down to only these 2 capabilities. But there's a lot that we can explore in this project, definitely.
Cool. And we have time for one last question. In the last 2 years, we have seen multiple works on re-evaluating KGE models. What would you suggest as the best way to compare different KGE models in the future? Is a leaderboard necessary?
A leaderboard, maybe a leaderboard for capabilities. And that's why, like, we think the addition of this project is that we want to highlight the importance of capabilities. Like saying that a model is good or bad right now is based on the MRR, like leaderboard over like a general test set, like the free-based test set. But since these test sets are full of different relations, different entity types, a lot of different things within them, it's difficult to tell where the models are succeeding or failing at. So maybe if we have different leaderboards for specific capabilities, then we can learn more about these models and evaluate them correctly in this way.
Okay, I think that's all the time we have. Thank you so much for this great talk. I saw like flashing in front of me that on Gather there are some noise issues. We will try to take care of it, and hopefully all of those on Gather can also try to pay attention and help one another. You can always move like away from the whoever is not muted, but I don't know exactly what's going on there. Anyway, so hopefully this will work out. We do want everyone to enjoy the talks. So our next presenter is Arye, and he will present the next Outstanding Paper Award, Psycho, Hierarchical Cross-Document Co-Reference for Scientific Concept. So, take it away.
Thanks, Jonathan. And hi, I am Arye Katan, a PhD student at Bayern University. And I represent Psycho, my internship project at AI2, which became a collaboration between AI2 and Barina. As a motivation for this work at Semantic Scholar, we are interested in enhancing the exploration of scientific literature by more advanced applications, such as faceted search and recommendation, automatic knowledge graph construction, author recommendation, and many other applications. And all these applications require the ability to link scientific mentions across different papers. And to see why, let's illustrate with the faceted query by example. This is an advanced search engine where instead of leaving the user searching over free text, here's the input is a snippet of a paper highlighted by the user. Then the system will leverage the raw context to find more precise results. So for example, given this query, image generating in machine learning, relevant results should include papers about the AI task of image generation, and image synthesis is another way to say image generation, so it's a good match. And conditional image generation is also a good one because users are interested by subtask of the query image generation. However, image generation from different domains, such as neurological studies or imaging technology in plants, are not relevant in these results because they are different domains, even though they are lexically similar to the query. So here we can see a few fundamental problems. First, lexical diversity. And here, because there is different ways to express the same concept. And also hierarchy, because conditional image generation, subtask of image generating, or ambiguity when mentions refer to different concepts depending on the concept, as we have seen here with image generation. And another typical application where we see the exact same challenges is author matching, where we would like to identify when authors work on similar or related task force methods. So given two authors, we can extract exhaustive list of mentions from the papers, but long flat list are hard to process and compare because of the same problems that we have seen before, lexical diversity, natural language inference, and textual entailment, or ambiguity in network architecture in operating system is not network architecture in deep learning, or also hierarchy, cross-document language modeling is a specific pre-trained language model. So we see all these challenges on this application, and they also arise for many applications. And ideally, we would like to resolve all these three challenges together and get a better structure of these areas of research, but for all authors individually that capture both reference and hierarchy instead of long flat lists. So in previous work, cross-document reference resolution is addressed only for event and entity reference, and there is no data set in science with abstract concepts. And for the literature and scientific domain, people use coreference resolution, but only on the single document, and hierarchical relations are often addressed through the task of hypernym relations between individual mentions where they appear in the same sentence. But there is no hierarchical relations between clusters of mentions across multiple documents. So our goal in this task is to foster research on this area, and we are interested in addressing all the challenges together. So for that, we define a new task that we call hierarchical cross-document reference resolution, where the input is a corpus of scientific papers with extracted mentions of methods and tasks. And then we need to first create cross-document clusters of scientific content, and then build a hierarchy over the clusters. And we introduce a notion of referential hierarchy, and it simply means that when we mention one concept, we also implicitly referring to its parent concepts, even though we do not explicitly write their parent concepts. For example, BREP model enters a reference to neural language model, even though we don't write explicitly neural language model. And to illustrate our task, given these mentions in context from different papers, and the first goal is to cluster similar mentions, here self-driving cars with autonomous vehicles, and also categorical image generation with class conditional image synthesis. And then these clusters of mentions falls under the parent task of generating images, and these clusters falls under the domain of computer vision. And to sum up the novelties of our new task compared to previous work, we are the first to address cross-document reference over scientific concepts. As we have seen before, cross-document reference brings its own challenges because the papers are written by different authors around the world by different time. And we also define the first task of referential hierarchy over reference clusters. And put together, our task requires addressing jointly fundamental challenges of NLP, lexical diversity and ambiguity, and also hierarchical relations. And to make our task a research task, we construct a new data set, evaluation metrics, and also develop baseline models. Let's start with data set and evaluation. Annotating a data set for this task is very challenging because there are millions of papers in computer science. Also, the task requires solid knowledge in computer science and familiarity with academic papers. The annotation itself involves a high cognitive load for the annotators. So to reduce the scale of papers, we leverage two existing resources and distance supervision methods to create candidate mentions from different papers. So we use papers with code, and also we construct automatically a very large hypernym graph from a corpus of papers. And then we hired expert annotators and trained them extensively with both automated and manual feedback along the way. And we use Corefi, which is a simple and efficient annotation tool for reducing cognitive load that we published last year at EMNLP. And then we obtained a large-scale data set with 20,000 documents and 26,000 mentions. And with these numbers, Psycho is 3 times larger than ECB+, the main benchmark for cross-document reference resolution. And in addition, now for the evaluation metrics, in addition to the common coreference evaluation metrics, we define new metrics to address our novel setting of hierarchy over clusters of mentions. So the idea is simple. We aim at weighting the mistakes of the system according to the distance in the hierarchical graph of clusters, as we can see here, but I won't get into the details. Please refer to the paper for more details. And moving on the models, we observe that deciding whether two mentions should co-refer or have a hierarchical relation is not straightforward. For example, artificial neural network and neural network are equivalent, but definition extraction is rather a subtask of information extraction. So we develop a single model where we formulate the problem as a multi-class objective for all pairs of mentions. And specifically, we cross-encode all mention pairs with their surrounding context and entity markers, as we can see here in the bottom of the screen. And in order to leverage wide surrounding context, we use two transformer models, Longformer and CDLM, which is a recent transformer for multi-document tasks that will appear in the upcoming EMNLP. And the results show that our multi-class cross encoder outperforms other baselines based on existing models according to all evaluation metrics. That being said, the task is not solved yet, because in the paper we have some analysis that show that the models often rely on lexical clues. As a result, the model failed at linking diverse mention, manual annotation with human labeling, or type 1 error with false positive. And the model also made erroneous links between the generic term of information extraction from any support with the NLP task of information extraction, while they refer to different concepts, or kernel in operating system with kernel in convolutional neural network. And this reveals that our task is very challenging and requires deep knowledge in computer science to understand the meaning of scientific mentions. So there is a lot of potential room for improvement by future models. And to conclude, both our dataset Psycho and models are available on Hugging Face. And that's it. And now I would love taking your question.
Great, thank you, Ali. Yeah, that was a great talk, and thank you for this resource, this benchmark. So we have a few minutes for questions, so let's start. Is this corpus from a long time period? Could you use it to see how different concepts are renamed through time?
That's a good question. It's indeed from a long time period. We have papers from 20 years ago and also recent papers, but we don't have necessarily the link between how the task was named before and now how we name the task there nowadays. So
but the papers are maybe the papers are time-stamped.
Yes, and we have that in the metadata of the data set, all the papers of timestamp. Yes.
Great. Next question. Is this task good for evaluating transformers that work over long sequences, long documents?
Maybe, because it depends on the required context to solve the task. So in our experiments, we have seen that if we give to the model a long context, it's good, and the model is getting better the more that we give context. But there is some limitation. If we give to the model all the paper, it won't help the model to make the right decision if it sees a hierarchy of co-reference. So in a normal setting, the paragraph of the mention should suffice for solving this task.
Okay. Can you comment on the remaining challenges and what are promising ways to tackle them?
Yeah. So remaining challenges for this task is how can we maybe solve this task, but without using all this training data, maybe using some supervision, that distance supervision, or how can we incorporate the metadata of the paper, such as conferences or authors and title and citations of the paper into the transformers models to improve results. Maybe it can improve because we have seen some clues in the titles of all the conferences. So it can also help the model if we learn to use them good.
Great. And I think we can have one last question. Compared to other domains, how is the scientific domain different? Can your approach generalize to text from other sources as well?
So compared to other domains, so this is a good question because we also thought about this question: how can we extend this work on, for example, the news domain? Because, for example, events can also be hierarchical. We have events and sub-events. We have the war during a long war. We have different battles in the war. So the task itself can be formulated in other domains, such as news with events and sub-events. But the task itself and the resource itself the challenges of the task are very different in scientific domain and news event, because here we are talking about entities that are very abstract, such as information extraction or scientific concept or text summarization. And these terms are very abstract, or very different from entities or events in the news domain, such as people or location, etc. So the task itself can be indeed formulated in other domains, but maybe we should also annotate data for this new domain and down port this resource to this model train on this data to other domains. That's my thought in this question.
Great. Thank you for your great work. And now let's move to our last talk in the session from Huru Xiao, manifold alignment across geometric spaces for knowledge base representation learning. So whenever you're ready.
Okay, I'm ready. Can you see my screen now?
I don't.
No, I don't. It's not being shared right now.
Okay, let me try.
Yep, we can see it now.
Okay, can you see my slide title?
Yes.
Oh, okay. Hello, everyone. This is Hui Ru from Hong Kong University of Science and Technology. I will introduce our paper, Manifold Alignment Across Geometric Spaces for Knowledge-Based Representation Learning. The authors are me and my supervisor, Yang Qiu Song. This is the outline of my presentation. First, I will briefly introduce the motivation of our work. Our work focuses on the knowledge-based representation learning. As we know, knowledge bases have multi-relations with distinctive properties. Most properties can be handled by the Euclidean embedding models. However, transitivity is a special property that cannot be modeled efficiently in the Euclidean space. Instead, the hyperbolic space characterizes the transitivity naturally because of its tree-like properties. In the meantime, the hyperbolic space reveals its weakness for other relations. Therefore, building a representation learning framework for all relation properties is highly difficult. In our paper, we propose to learn the knowledge-based embeddings in different geometric spaces and apply manifold alignment to align the shared entities. Different geometric spaces model the various relation properties and the various local structures of the knowledge base, while the manifold alignment framework provides a way to incorporate the local manifold structures of different entity sets. Next, I will give our task and problem formulation. We evaluate our approach on the out-of-taxonomy entity typing task. A simplified example is shown in the figure. The knowledge base can be divided into the taxonomy and the knowledge graph. The taxonomy has transitive relations, while the knowledge graph has multi-relations without transitivity. Our task is to predict the type for the out-of-taxonomy entity. In the taxonomy, the type set contains types such as scientist. The entity set contains entities such as John Lennon. The directed edge set infers the transitive relation, such as John Lennon instance of artist. In the knowledge graph, there are entity set, relation set, and triplet set. The taxonomy and the knowledge graph have some intersection entities, such as George Harrison in the figure. Our task is to predict the type for the new entities which occur in the knowledge graph, but not in the taxonomy, such as Eric Clapton in the figure. The task is important in practice since some entities are missing in real-world taxonomies, but occur in the knowledge graphs. Manual labeling is unpractical because of the large number of new entities and the high labeling cost. Then we come to our method. The main framework of our method involves 3 parts. The first step is to pre-train the taxonomy by hyperbolic embeddings and the knowledge graph by trans-E. For the pre-training models, We choose the hyperboloid model to pre-train the taxonomy because it can alleviate the numeric instabilities of hyperbolic embeddings. For the knowledge graph, we use the classical and the effective embedding algorithm CHANS-E. Next is the core part of our method. After pre-training, we apply manifold alignment to align the hyperbolic embeddings of taxonomy entities and the Euclidean embeddings of knowledge graph entities. Given the pre-trained embeddings of taxonomy entities IT and knowledge graph entities IG, our objective is to learn the projections phi, which map the embeddings of IT and IG into a shared manifold. First, we constructed the binary correspondence matrix W using the intersection entities. Next, we constructed the binary correspondence matrix W. Next, we construct the adjacency graphs for IT and IG by k-nearest neighbors from the point-wise distances within the two entity sets. Then we constructed the similarity matrix using heat kernel. Then the manifold alignment loss is defined as Lm. In the manifold alignment loss, the first term preserves the local manifold structures within each original entity set. The second term minimizes the distance between the corresponding entities, that is the same entity in different entity sets. Mu is the weight to balance between the two terms. Using the Laplacian eigenmaps, minimizing Lm is equivalent to solve a generalized eigenvalue problem of the joint graph Laplacian. Let V0 to Vd be the solution ordered according to their eigenvalues. Then V1 to Vd are used for the aligned embeddings. You can refer to our paper and the appendix for more details of the generalized eigenvalue problem and the proofs. Following the above procedure, we project both entity sets into a shared manifold. The aligned embeddings are learned by preserving the original manifold structure and recovering the correspondences. They provide correlations between the taxonomy entities and the knowledge graph entities. Next, we link new entities and retrain the completed taxonomy. After we obtain the aligned embeddings, we compute the pairwise distances of all entities in the shared manifold. From the pairwise distance, we further connect the taxonomy entities and the new entities by KNN, and thus have the new edges. With the new edge set, we can retrain the hyperbolic embeddings of the completed taxonomy with original directed edge set ET and the new edge set EN. Note that EN is different with ET since ET is a set of original taxonomy edges, representing the transitive relation among types and entities, while edges in EN reveal the similarities between entities. To differentiate them, we regard the edges in EN as weighted undirected edges during retraining. Next, I will present some main results of our experiments. We constructed two taxonomies, Yago WordNet and Wiki Objects, and one knowledge graph, Yago Facts, from Yago 3. We compare our method with traditional KG embedding models, hierarchy-aware Euclidean methods, and multi-relational hyperbolic models. So here are the entity typing results on various dimensions. We can see that GeoAlign outperforms the baseline significantly, and the Euclidean models have big improvements in higher dimensions, but not comparable with the hyperbolic models. The hyperbolic models require much lower dimensions. And we also find in this experimental setting, where the training rate equals to 0.5, the performance of Morph, Attention H, and GeoAlign are close under this. So next, we evaluate on the small training rates. We can see that when the training rate is small, GeoAlign outperforms Morph and Attention H a lot. And with the increase of the training rates, their performances get more and more similar and converge to stable. We also conduct some interesting ablation studies. The ablation study on the retraining step demonstrates that after manifold alignment, the retraining of the embeddings with the added edges incorporates more structural information of the taxonomy with new entities and improves the entity type performances. the retraining had some impact on reconstruction of the original training taxonomy, but the compromise is acceptable. And the evaluation study on the hyperbolic models shows that dual-align hyperboloid surpasses dual-align pancreas a lot, especially on the out-of-taxonomy entity typing task. Finally, it is the conclusion and future work. In this paper, we propose to learn the embeddings of knowledge bases in different spaces and apply manifold alignment across the geometric spaces to build the projection. The empirical results demonstrate the superiority of our approach, especially in low dimensions and on small training rates. Future works include the exploration of broader types of geometries for learning knowledge-based representation and more effective approaches for aligning multiple manifolds. Here are some main references. And thank you for listening to my presentation. Questions are welcome.
Hey, Anson, you're muted. Yeah, sorry.
So we have time for a couple of questions up here. You can ask in the meanwhile. So just a clarification question. Are the entities with the different types of embeddings identical? How much intersection is there between the entities with a different type of embeddings?
Okay. Actually, the entity sets of the taxonomy and the knowledge graph are different. So there are some intersection entities, but they are not the same. In our paper, we give the statistics of the intersection entity numbers.
Okay, and maybe one last question. Can you comment on the runtime of your approach compared to existing approaches?
Okay, sure. Because the our framework involves the pre-training, manifold alignment, and the retraining. So actually, the runtime of our approach is about twice training time with the existing hyperbolic embeddings. And we find that the manifold alignment step itself does not cost too much runtime compared with the training of the hyperbolic embeddings. So I admit that the runtime of my approach may be about the twice of the existing models.
Great. Thank you. I think that's all the time we have. So thank you very much for your great work. Again, warm congratulations to all the authors who won the paper award. And if you have more questions, we will have a poster session at the end of this day, and you're welcome to chat with them at the poster session. This concludes the outstanding paper session, and we will move right next to our next invited talk, the first invited talk of the first day. And it's a pleasure for me to introduce Tim Kraska. Tim is an associate professor of electrical engineering and computer science at MIT at CSAIL. He's the co-director of the data system and AI lab at MIT and co-founder of Einblick Analytics. Currently, his research focuses on building systems for machine learning, which seems to be the focus of our talk today, and using machine learning for systems. Before MIT, Tim was assistant professor at Brown, spent time at Google Brain. He was a postdoc at UC Berkeley after getting his PhD from ETH Zurich. Tim is an Alfred P. Sloan Research Fellow, received numerous awards, including VLDB Early Career Research Contribution Award, the VMware Systems Research Award, and NSF Career Award, and several Best Paper and Demo Awards at VLDB, Sigmod, and ICDE. So without further ado, I'm excited to listen to what Tim has to tell us today.
Thank you. It's definitely my pleasure to be here. Let me just directly dive in. So like my research is mainly focused on either applying machine learning to systems or building systems to make machine learning, in particular data science, more accessible to a broader audience of users. What I'm talking here particularly about is a system we developed like starting, I think, in 2014. So it has been a while, with the goal to make data science more accessible to a broader range of users. And nowadays, the term for that is citizen data scientist. So it all started actually almost with DARPA, who approached us very early on because they had the vision to put a data scientist in every single operational center they have. And they quickly figured out that they can neither attract enough data scientists, or simply also, like back in the days, not enough people to go around to fulfill this vision. So what they really were after is like making their workforce more data savvy. And as you can see at the rest of the talk, like this is a little bit of an outlier talk because I'm on a much higher level. It's not directly related to a knowledge graph. It's more like how can we make data science broader accessible and empower more people to make use of it. In particular, in the case of DARPA, they were focusing, for example, on intelligence analysts who are currently using a lot of Excel, do a lot of manual work, for example, to analyze conflict data, and they wanted to empower these people to use like more of the advanced techniques, for example, text classification and other things. And when we started this project, actually, we encountered many more personas like that. For example, there was a HR specialist who was wondering if like she can develop a model to like determine if a worker in the manufacturing line is at risk of leaving. Or we were talking to a manufacturing manager who was like thinking about if he can build a model based on the data he has to predict if a car will be actually delivered on time. Or we have an iteration specialist, like she was analyzing tickets and wanted to figure out if there's a way to prioritize what to focus on in any given state. So there are plenty of use cases. Mostly these use cases are like driven by 1-2 people in the beginning. They are not like highly mission critical. It's not like that you want to, for example, build a new image classifier and roll it out to thousands of users and that's your core business. Those are more like things where you try to improve something here and there. But at the same time, like those use cases provide a lot of value, but they struggle to get the attention, for example, of the data scientists. And so when we talked to these people, we heard like a bunch of challenges they were mentioning. Far most importantly, they were saying that the current tools are inadequate for them, and they are like normally focused on data scientists who have much more expertise, so they required something different. People were complaining about that, like the back and forth between actually the people who have the problem or want to build a model and the actual data scientists is painstaking slow, because it takes a lot of force and back to get on the same page, to understand how the data looks like, to clean the data actually as a team, because data scientists tend to have like a deep understanding of the techniques, but not necessarily the domain, let's say the data you have, whereas the domain experts, it's exactly the other way around. Nowadays, there are a whole bunch of like tools out there for creating no-code solutions. At the same time, like we heard that like just pure no-code is still an illusion. It gets you way too quickly to the limits. And then in the moment you use like no-code tools, maybe with some Python, and there are like a bunch of different tools, you have a challenge that you constantly have to import and export data between actually different tools you have, which particularly hinders a quick iteration on a problem. And so like normally what you want to do is like clean the data just enough that you can build a first model over it, and then you might detect like new data quality problems, so you have to go back and so on. And all this together hinders timely decisions, and last but not least, like the standard way of communicating any results is still PowerPoint. And normally there's a big disconnect between how results are presented in PowerPoint and where the actual analytics is happening. So these are like challenges we heard from the people we're talking to. At the same time, there's really no shortage on visions on how data science actually should look like. Particularly Microsoft put a video out like a few years back on how they see data science should look like. And if you watch this like little clip here, what you see is actually a team getting together, working on a problem. Results appear like in real time. It's really a collaborative effort between domain experts and data scientists. And if you take this vision, and this video is now from 2015, and you compare it to how still data science looks mainly today, you get a very different picture, right? So mostly it's still a single person in front of a Python notebook, even if you take the latest and shiniest tools, which tend to be like either visualization tools or workflow engines, it's still focused on a single user. So why is this a challenge again? It's like mainly because things don't happen in isolation. And I'm drawing here actually from like an industry partner we are currently working with. So it's like the previously mentioned production line manager. He wants to forecast if a car will be delivered on time. Then the first thing he did, he talked to some data scientists, and they actually told him, oh, that's a classification problem, actually not a forecasting problem, even though it's time series data. Then the next thing is like, oh, we just installed, like, let's say, a new machine in the manufacturing pipeline, and now all the error code changed. So you need to consider that when you're building the model. Then maybe he gets something running, and suddenly people get more interested in it, and I say like, oh, can you consider also staffing in the modeling? And so overall, you get more and more people involved. And while you're doing that, the whole process, like almost as more people you have, the more it slows down, because aligning people from different teams takes time. It's extremely hard. The analytical lifecycle requires a lot of different tools, as mentioned before, and expertise in switching between them. And then in the moment you have like a little bit of larger data, or you do complex computation, it essentially destroys any collaboration you might want to have, because nobody wants to stare at the screen and just wait for results to pop up, particularly if it's like longer than a few seconds, right? Like, let's think about an automated machine learning tool. You spin it up, you want to get a model back, and everybody is standing in a meeting room looking at the screen for 10 minutes waiting for a result. So when we started North Star, actually, we tried to address these challenges, and our hope was to build something from the ground up to create a collaborative environment for citizen data scientists so that they can actually work together. And we started out by addressing like on how we can bring people together, particularly using a normal interface. And the result of it was North Star, which was like our first research prototype. Originally, we designed the prototype to particularly run on large interactive whiteboards, like the Microsoft Surface Hub you see here on the screen. The key ideas behind the interface is actually that it combines different aspects you see nowadays in different tools into one coherent way. So most importantly, there are tools out there for data visualizations. They're very easy to use, but they essentially don't allow you to create complex workflows, data cleaning, and other things. Normally, if you have, for example, a tool like Tableau, there are other tools up front you have to use in order to get the cleaning done, for example. So instead, what we did in our interfaces, we tried to take the aspects of a visualization tool like Tableau and combine that with aspects of like a workflow engine, like, for example, what you nowadays have in Alteryx, Azure ML Studio, and so on. So by combining the two, now you can visualize very quickly data, but you can also build more complex workflows. And then we took these two concepts and like tried to put something in there so that we enable more people to actually collaborate together. And our approach to it was that we had an infinite canvas where you can lay out visualizations, arbitrarily connect them to complex flows. And nowadays, like, there are some other tools out there which have similar concepts, for example, Miro and Figma, which are not designed for analytics per se. They're more like brainstorming collaboration tools, but they also have this idea of like an infinite canvas where you work together with. And we just build such an infinite canvas for data. The whole concept we call just like visual data computing, and as mentioned earlier, it combines the aspects of just like a workflow engine with a visualization tool with modern collaboration tools like Figma, for example. So recently we are like commercializing it as Einblick, and I will mention that later on. So if you go to einblick.ai, you can actually try it out by yourself. But like the user experience was really something which we completely rethought for like collaboration pieces, and we wrote a bunch of papers on about it on how that interaction paradigm works and what the advantages are, and as well as the disadvantages. So moving on, as I mentioned before, the other aspect is like that there are a lot of different tools involved normally in a pipeline, and So like here I'm taking the typical pipeline as defined by Gartner, which consists normally of gather data, preparing, then exploring it, model building, model production, and then communicating results. And as you can see, for the different stages, there are currently like a lot of different tools involved, which specialized on a particular step in this like data pipeline in order to get some interesting results out. The downside of that is like now I have to import and export data between a lot of different tools, which causes friction and hinders like very quick iteration. So with Nostr, we actually try to take a little bit of a different approach, again, by saying that like broad capabilities are way more important than specialization. So by no means, when we started to design the platform, did we provide all the functionalities these existing tools do. But our thought was like, if we get like 90% there with like the most common things you anyway find in scikit-learn and co, we can create a platform which easily allows you to go all the way through the pipeline and quickly create a prototype and then iterate on it. And then if you need a specialized tool for any of the steps, let's figure out a way on how we can actually integrate it. The next one is like the slow computation, and this is particularly interesting because when we developed the interface, we quickly found as well that if you don't address the interactivity part, essentially like the interface and the collaboration piece doesn't work. And here I'm only talking for our backend piece on how that particular works. So actually there has been studies around like what the impact of delays are on the exploration process. The most well-known one was like done by Jeff here and his students on the effects of interactive latency and explorative visual analytics. And what they found is like even if you have a increase in latency from just like 500 milliseconds, so it's like the results take longer than 500 milliseconds to produce and incurred a significant cost, decreasing user activity and dataset coverage rate while reducing rates of observation, generalization, and the numbers of hypotheses created. So even a small delay of like 500 milliseconds has a significant impact. What we found more is like if you have larger data sets, this gets way, way worse because you're often not talking about 500 milliseconds increases. You easily talk about a couple of minutes. So we needed a way to encounter that, and as part of the Nostr project, we developed the first like interactive data exploration accelerator, which in the end you can think of as a sample management system. So how that works is that in the moment you connect to a data warehouse using Nostr, we have the accelerator sitting in between, which automatically takes samples from the underlying data source and then stores the samples into main memory, but it gives you results as the samples come in. So normally what like you take is like a small sample, we give you an initial result on the small sample, and then in the background make the sample larger and larger until it eventually converges to a final result. Interestingly enough, the same approach for like increasing the sample also works for like complex operations, like for example, automated machine learning tools, where you can play a very similar trick of like first running something over a sample, which might not give you the best possible answers, this might tend to overfit and so on. And then in the background, you increase the sample size so that you actually increase the accuracy of the model and so on. There are a bunch of like techniques which factor into that. For example, for automated machine learning, you need to make sure about how you deal with the training and test split as your sample size increases, and a whole bunch of like other corner cases you have to be really carefully with. The other interesting aspect is like in the moment you do complex transformations, it becomes also a question on how you manage your different samples you have, because maybe not all the data might fit into your main memory. And so you need to figure out the best possible way to what samples to keep around at what point in time, as well as how you combine the sampling with like techniques like predicate push down to the underlying data source. So for example, if I do a complex transformation, I do again that in a sample-based approach, but then I might keep two samples now around afterwards, one the original one, another one after the transformation, so they have a very quick access to both of them. The result of that is now that you get a much better user experience. So this is like an example of just like using the flight data set, which is well known and stored on Amazon. And it's just like showing a version of North Star, now called Einblick, on it, where like first you have the distribution of the data over the year, and then you want to do a filter expression by a particular year to see what are the most common destinations in the data set. And on the left side, you see the progressive computation. And after 400 milliseconds, you already get like a rough estimate of the distribution of the most common destinations. Whereas on the right side, we actually turned off the progressive approximation engine. And so as you can see now, the data is actually sucked in from S3. It takes time. Even after like now 24 seconds, there's still no result. There's like the left one more or less already fully converged. There's still some outliers coming in. As you can see, it varies slightly still on the left, but it's pretty stable overall because sampling is such an efficient technique. And then after 6 minutes, on the left side, it's completely converged. And on the right side, it takes a little bit longer. It takes like 6 minutes and 12 minutes. The reason why in this case it takes longer on the right side is that like Einblick or North Star already had like some samples in cache before it started. So overall, the result is that we completely rebuilt the platform, or like rebuilt the data analytics stack to create this like very interactive environment where people can collaborate together. We started really with the visual front end. Based on that, we figured that we had to redesign the entire back end. And we also had actually to rethink many involved algorithms. For example, we have our own interactive automated machine learning tool, which I don't think I have enough time to go into detail with, or we have our own key drive analysis, which helps users to more quickly discover interesting insights. So coming back to the original list in the beginning, so over the 6 years we were working on it at MIT and Brown University, we tried to find solutions for the different things we heard early on with the conversations with our customers. Or now customers. Back then they were just like industry partners. So the first thing is just like current tools are like not suited for business users or to turn them into citizen data scientists. So we really tried to build a platform from scratch with them in mind. It has this concept of an unbounded canvas to support in person, and later we also added remote collaboration capabilities. We make it very easy for you to integrate your own code and even build your own visual operators. Our approach was like that we have an end-to-end like take on combining all the operations you need, from data cleaning to model building to validation and so on, in a single platform, without being potentially the specialized platform or the best like piece for any of them. But at least you can do very, very quick iterations. And it turns out that in many cases, it's more important that you iterate quickly about cleaning and model quality, for example, rather that you have the best AutoML tool out there. So overall, together with the progressive approximation engine, this allows you to make your much more timely decisions. And this is something we added later on as part of the company. We integrate very deeply with PowerPoint because we felt like we cannot replace it. So actually what the platform allows you to do now is export to PowerPoint directly and keep everything you have exported in PowerPoint up to sync with new data, new analytics, and so on with the click of a button. So it's not pictures we integrate there, it's something a little bit more advanced. Everybody here, I encourage to just try it out. We would love to hear your feedback and see what you think about it. Just give it a try. Like if you sign up today, you can use it like for 14 days for free, and even afterwards, like particularly with academics, we tend to give free licenses out as long as you promise to write a blog post for us. So where's the research going right now? And so like the platform itself is set like we commercialized it. Now at MIT, we are looking beyond that, and in particular what I'm interested in is like trying to automate even more and make it even easier for users. And so we are trying to build like intelligence assistants, which have like a citizen data scientist and then guides them through different steps and, for example, warns them about problems. There are like many different things we are currently thinking about, from how much can we automate the process of data cleaning, can we suggest automatic insights, and there has been some work from other groups on that, but there also there are certain challenges with it. Natural language interfaces became pretty interesting to us. However, what I want to focus here on for the last few minutes I have is like protection from common mistakes, because these tools like, for example, North Star actually increase the risk that you find things by chance, which might actually not be statistically significant. And this is like not a new phenomenon. It's just like it's out there already for quite some time. There's clearly an increase of risk of questionable findings. And just to name a few of them, which I encountered lately. So for example, there was a study showing that like a glass of red wine is equivalent to 1 hour at the gym. I'm trying this now for over a year and I still don't see the results. There was another study showing that like the secret of winning a Nobel Prize is eat more chocolate. Unfortunately, this study didn't show that this also holds true for the ACM Turing Award, so it's a little bit less relevant. There was another study showing that the secret of a longer life for man, that they found it. The bad thing is that castration is the key. So as you can see, there are like a lot of this like different findings out there. And part of the problem is like in the moment you have a data set, it's nowadays so much easier to run like thousands of hypothesis tests over them and lose a little bit of track about like, okay, where like are actually like what is actually statistically significant, where like risk factors coming from, how many questions am I allowed to ask over the data set. And tools like North Star, but also take other ones like Tableau and Co. actually increase the risk factors in the end because they make it so much easier to ask more and more questions. And so why is that the case? The main reason is that like every visualization you have is actually in the moment it provides you any insight, an implicit hypothesis test. If it wouldn't be the case, then you just have to take them as pretty pictures without any meaning about random facts. So let's, for example, you see that something is correlated because you see like one plot bar chart is higher than another. You take a conclusion from it. You say like, oh, this thing is actually like, for example, impacts more men than women. In the moment you see that you have this conclusion, implicitly you're doing hypothesis test, just you don't run it explicitly over it because you assume, okay, this difference probably counts for something. If you just took out the bar chart and you see the difference and you say like, oh yeah, there's a difference, but it doesn't have any meaning. But again, then it's just like, it's this pretty picture without any conclusions. And that's fine. You can have as many pretty pictures as you want. And then the moment you draw something from it, even from a visualization, implicitly you're doing a hypothesis test. And so now it's more visualizations you look at, the more things you're implicitly testing. So, I mean, like there's no surprise, and there are many of other examples out there. So we ran like a little study where we did a survey on Amazon Mechanical Turk. We asked people like a bunch of random questions, and then we looked for interesting insights. So actually we gave the data we collected to like students of ours as a user study and asked them to find some interesting facts. And for example, one goal they had was find a good indicator if somebody knows who Mike Stoneberger is, like one of the Turing Award winners a few years back. Like some of the user candidates or the user studies came back with some very interesting findings. For example, one of my favorites is still that like after searching for a while that they found if you often go to the sauna, you are more likely to know who Mike Stowbreaker is. And like clearly, if you look at this example, it's clear that like, yeah, this correlation is more than questionable. And they just found that by using the visual tool. Even better, they even did the statistical significance test afterwards and found that still statistical significant. So now we are exploring new techniques to mitigate this problem. And particularly, we are trying, for example, to figure out if we can warn the user automatically if the chance of like finding something by chance gets too high. So we have a prototype we developed at some point, which like looks at what you do on the screen, tries to infer what hypothesis conclusions you might be drawing from it, and then keeps track of them and does in the background multiple hypothesis control. This is not perfect. This is a best effort approach, but we believe that the best effort approach already provides you a lot of value, rather if you would do like essentially nothing and just hope for the best. So with that, I'm essentially at my end. So it was a pleasure to be here. Like probably a little bit of like a more exceptional talk, focused on citizen data scientists rather than knowledge graphs. Again, we would love to hear your feedback if you try out the platform, and I'm more than happy to take any questions.
Thank you, Tim, for this very inspiring talk. We have a few minutes for questions, so let's jump right in. Can you say a bit more about the AutoML part? It looks really cool. It seems difficult, though, to do training and evaluation in 500 milliseconds.
That's very true. So actually, I had like I skipped over the slides. I had a few slides prepared on how our AutoML tool works. The AutoML tool actually considers the sampling from the get-go. And so what we do is like we take samples, we train over them, and then we look into the regime of overfitting versus the sample size. And if you can estimate if the larger sample, the model would actually perform better. So like essentially you take the error over the training sample as well as the test sample, and that gives you a clue about if they potentially will get better over time. And that's what we leverage there. And then there are a bunch of other machinery in there. For example, normally, so like it also has an approach from meta learning. So in the beginning, we try out simple models. For example, we often like boosted regression trees as the model of choice because they're very fast to train and they work very well. And as time progresses, we try more and more risky models up to then transfer learning things, because that's like takes much longer. They can be really good, but you need more time for them. So they're probably not the best thing you should try out in the beginning when you are just experimenting and see what works.
And that's very cool. Next question, does the North Star tool deal with unstructured text, or is all the data structured?
We have a lot of text support by now. So what we don't do is images, video, or any strange data like DNA and other stuff. But text data, like it's a pretty common case by now. So there are capabilities built in.
Great. The next question is, very cool. Did you do any user studies to show that the tool makes it easier to detect fake data or any errors in pre-processing and so on?
Yes, we did. We did a bunch of user studies. For example, we have one separated one on the impact of the progressive reapproximation engine. So how does it impact the overall behavior? We did some initial ones for the hypothesis testing part I talked about last. There's an ongoing user study right now regarding like how much does it help you overall? So how much faster are you able to get to an end-to-end solution using our approach versus other approaches? So for example, like a Python notebook or K-MIME or other things like that. So this one is not published yet. That's ongoing right now. And part of it is also like, for example, you present them something and how quickly do they find a problem in the feature set? Right, like let's say information leakage.
Yeah, this seems incredibly useful. Also, given the last part of the talk. So we have time for the last two questions. Is the exploratory data analysis component also learned from real user activity with data exploration systems?
I'm not 100% sure if I understand the question. What part of it? Is the exploratory data analysis component also learned from real? So like the automated machine learning part actually has a knowledge base in there. So it's like it uses meta learning to figure out what order, for example, to try what models for. The data exploration part right now is like we have the key driver analysis. That's a statistical technique which actually considers hypothesis testing. We don't do right now insight recommendation. So KDA is a form of insight recommendation. So what it does is like, for example, you have customers who accepted a promotion, customers who don't, and you're trying to automatically figure out what makes a customer to accept a promotion. So what are the differences between the two populations? But how we solve that is a form of automatic hypothesis testing. It's like not a full-fledged insight recommendation.
Great. And last, is the system that tracks hypothesis testing, do you track the gaze of the user?
We don't, unfortunately, yet. I think there are a lot of opportunities there. So like that, right now we have just a very simple heuristic to like infer what hypothesis the user might be drawing from a visualization. It's really heuristic based. I wouldn't say it's good per se. Ideas we thought about is like gaze would be an awesome one to explore, but also just like have, for example, like natural language recognition. So if the user would speak out in a meeting, oh, this looks interesting, you can infer probably a lot from that, right? And so like hearing what the users are saying, I think would be a really cool addition to it, but we haven't done it yet.
Cool. This is really very impressive. Thank you so much.
Thanks for having me.
Yeah, that's all the time we have. I hope Tim will join us in about 40 minutes or 35 minutes in the chat room. And I will pass the torch to Danchi now, who will introduce our next invited speaker.
So next is my great honor to introduce our next speaker, Hannah Hajishurzi. Hannah is an assistant professor in the Paul Allen School of Computer Science and Engineering at the University of Washington, and a research fellow at the Allen Institute for AI. Hannah's research focuses on developing machine learning algorithms that represent, comprehend, and reason about diverse forms of data at a large scale. So Hannah has done a lot of great and influential work in question answering, reading comprehension, representation learning, green AI, knowledge extraction, and the conversational dialogue. And she has also won numerous awards, including the NSF Career Award, the Sloan Fellowship, Allen Distinguished Investigator Award, Intel Rising Award, and multiple Best Paper Awards. By the way, Hannah was also the program co-chair of AKBC last year. So Hannah, welcome back. So today she's going to tell us about her recent very exciting research on knowledge-rich, robust neural text comprehension and reasoning. So Hannah, please take it away.
Thanks a lot, Danchi, for the introduction, for the great introduction. I'm very honored to be back at AKBC, this time with an invited talk. I'm very excited to talk about our recent work on developing robust NLP algorithms. Vast amount of textual data is available online in many different forms. We have different forms of text, for example, in textual paragraphs, in a large collection of them, even across different genres like scientific text. We have text in conjunction with other modalities, like with visual data, or in a structured format, for example, scientific knowledge bases or Wikidata. Therefore, the problem of understanding text, comprehending it at a level that we are able to make reasonable conclusion and do reasoning about it is a really fundamental problem in NLP. People or researchers in NLP try to evaluate the progress in this important problem with different task applications, such as question answering or fact checking or textual entailment. But overall, the goal is, can we build AI algorithms that can generalize to new domains that require complex reasoning or when training data is scarce. How does current paradigm of NLP work these days? Most of you are familiar. I just want to give a quick review. We have pre-trained language models using some sort of self-supervised objectives. People have named them after Sesame Street characters, at least the earlier version. Then we have collected usually large-scale data sets in some of those kind of well-known tasks in NLP. For example, only in question answering, over the past few years, we have had a surge of data sets in many different formats and many different styles. Then at the end, when we want to solve some of those tasks or data sets, what we do, for example, in the task of question answering, we take the input, the question and the context paragraph, let's say, and then we pass them or encode them with our pre-trained language models, and then use the annotated data or the constructed data sets and train task-specific layers, or we call them fine-tuning. For example, for question answering, the goal is to extract the phrase that answers the question. But how about the type of questions or the type of tasks that require more complex reasoning? And in particular, it's really hard to collect data for them. Let's look at this question. What percentage of the Washington state budget has been spent on education over the last 20 years? How can we answer such question? Our first step would be some sort of retrieval, to go over web, find all the relevant passages that are potentially containing some sort of answer to this question. Then actually go inside these articles. They can be pure text, they can be tables, they can be graphs, or in conjunction together, comprehend them and understand what's going on. Then finally connect all these different pieces of evidence and then reason about it, answer the question, realize we actually want to solve this equation. Okay, so how can we build AI algorithms that address this type of question? So here, I'm going to present some of our recent work that kind of aims at getting to answering these type of questions and solving these type of challenges in AI. First, I will describe some of our recent efforts on building general purpose models for known tasks, in particular in question answering, in English and across different languages. Then I would describe how we can use knowledge in the form of a structured knowledge or kind of parameterized knowledge as some sort of distant supervision to guide neural reasoning. And then finally, if I have time, I will describe our very recent evaluation benchmark that enables cross-evaluating the capability of models for cross-task generalization. Okay. Our first work, we call it Unified QA. The goal is to build a unified model for question answering. As I mentioned earlier, we have a surge of data sets in many known tasks in NLP, especially in question answering. People start building and creating these different data sets in question answering because they have some specific assumptions about input and output. For example, they are looking at different types of context. They are looking at different formats. For example, some questions are multiple choice questions. Some are kind of reading comprehension style. Some are open domain, and so on. And these data sets are being explored and are being developed so that they are enabling researchers to explore some unknown reasoning challenges or some reasoning challenges that models were not capable of handling them. Here are the list of some of those data sets. Our solution is, or basically the question we are trying to address is, okay, we have all these different data sets, but there is one important observation. There is an overlap between the underlying reasoning abilities of all these data sets and formats within the question answering boundary. And the intuition that we have observed is that we can benefit from mixing all these question answering formats. we introduced unified QA, that is a general purpose question answering systems that works across different QA formats and data sets. And the intuition is that it sits somewhere between the pre-training stage and the fine-tuning. And it basically uses some sort of multitask learning to look at all the available instances of different question answering data sets, kind of that goes beyond, between pre-training and fine-tuning. Okay, so here is the concrete steps we've done. We collect question answering data sets in different formats. We have 9 data sets, including multiple choice, extractive, generative, and yes/no questions. We unify the format of all these data sets, or of all the instances within these data sets, into a text-to-text format. For example, if we have a multiple choice question like this, what causes sound, and then the list of choices, we basically concatenate them, put a separator between them. This is the input, and then the output is kind of the answer, which is the vibration. And then we use an encoder-decoder architecture. In our experiments, we experimented with T5 and BART, and then kind of trained the encodings of these input-output texts. And then we train them using multitask learning. There are 2 important things to note here. First of all, we train simultaneously on all these data sets. In particular, we've noticed that, or made sure that in all our batches, we contain instances from each of these training sets. This is different from a standard multitask learning, where we basically train one head per task. Here, we're going to combine all these different instances across all these different data sets. The results are really promising. Our first experiment was to show that unified QA, represented with dark blue here, performs almost most of the time better, or usually on par, with the dedicated models that are designed for those specific data sets that we trained on. Also, we have observed that unified QA generalizes really well to unseen data sets. Again, here the dark blue is unified QA, and light blue is the state-of-the-art on those data sets. Note that these data sets that I am listing here at the bottom, we haven't seen them during training. But nevertheless, we've seen that unified QA performed really well. And we kind of think that the reason is unified QA has seen a lot of kind of question and answer pairs before. So it's able to generalize to different reasoning abilities. Also, we have taken unified QA as an artifact and started to fine-tune it even further on new data sets, kind of going beyond the 9 initial data sets that we had in our batch. We have achieved the state-of-the-art on 10 data sets. Here I'm listing some of them. This is the previous state-of-the-art at the time that we were writing this paper. And these are the new results using unified QA. So the results are quite promising, and we show that the successful application of multitask learning within the QA boundary. One thing to note that people had explored this idea of multitask learning before, but here we argued that the choice of tasks are important. If the tasks are really diverse, then probably we'll see less effect or less impact of training them all together. This has had impact in the literature. Basically, we showed, other people showed that this is generalizable, and our unified QA achieves a state-of-the-art in other benchmarks as well, like science benchmark and so on. Also, people have taken this and applied it in the few-shot learning setup from Berkeley group, especially, that they showed that we can meta-tune language models and also they built Uniflow. We also have inspired future work in multitask learning across other areas, not just for question answering, but across different tasks. And for example, in various types of common sense reasoning. Okay, so these are all really great, but whatever I described was only in the English domain. So what happens if we want to go beyond English? And this is our very recent work, which is just accepted at NeurIPS 2021. And the idea is to build a unified multilingual question answering system. Okay, so let me first define the problem a little better. In English, we call a task open retrieval question answering when we are looking at it like this. We have some question like over how many species of trees can be found in the Saxon garden. When we call it open retrieval, we mean we want to cross-reference it with a really large collection of articles, in particular in Wikipedia. Usually the current approaches retrieve a few passages that are likely to contain the answer. And then a reader model that tries to read all these passages and then find out what is the actual answer to this question. And we are building, like this whole method is built based on Danchi's method, both for dense passage retrieval and her earlier work. But all of these are limited to English. This is really challenging because in non-English resources, we do not have annotated training data. People have observed this need, including our team, and I started building and creating multilingual question answering data sets. Two of them are called XOR-QA from my own lab and MKQA from Apple. But the thing that is limited in these data sets is most of the questions can be in any language, like they have 5, 6, 7, or even 20 languages according to different data sets. But the answers can be retrieved either from the target language, like the original language that the question was posed, or from the English Wikipedia. And therefore, the approaches that are designed to solve these tasks are as follows. For example, the question comes in Bengali. We're going to translate the query into an English translation, okay? Then we run an English QA system, which is our good old like retrieval reader modules, find the answer in English, and then translate it back to Bengali. Okay, so this works okay in these two data sets I mentioned here, but obviously there are a lot of issues. The first one is the accuracy of such question answering system is bounded by the accuracy of these two steps of machine translation. Moreover, who says the answer to a Japanese question should be found in either Japanese articles or in English? Maybe we could find the answer in other Wikipedias, let's say Spanish Wikipedia. So it's really important to build a multilingual question answering system that is able to retrieve and reason or read across multiple languages or kind of cross-lingually between different languages. So here is what we've done in this project. We basically have built a many-to-many cross-lingual answer retrieval and generation system. It does not use any specific machine translation or retriever modules. And it achieves the state-of-the-art in these two question answering data sets I mentioned, in particular in 26 languages. So how does it work? It's a single multilingual QA system. It follows the same pipeline as in English QA. It has a multilingual dense passage retriever module and also a multilingual answer generator module. And at the retrieval step, this is how it works. We have a question in any language that you want to, and then a collection of Wikipedias across many different languages. We're gonna encode them into some embedding space. So we have question encoder, we have passage encoder. And then at inference time, we're gonna do a maximum inner product search and then find the passages that are likely to contain the answer. It can be in the original language, it can be in English, or it can be in some other completely different language, okay? In the generator step, we take these collection of passages across many different languages and then generate the answer in the original language that the question was asked. Okay, so this all sounds really exciting, but the important challenge is in order to train both of these multilingual DPR and multilingual generation, we require to have training data, like cross-lingual training data, but that data is not available. How do we resolve this issue? We resolve it using an iterative training approach. In particular, we initialize the multilingual DPR training using the available kind of XOR QA between the original language and English, or original language and like the same Wikipedia. So we started training this multilingual DPR first. Then we train our generator using the DPR that we have already trained, but most of the time things are only between English and another language. Now we like to expand the data. How do we do that? We know there's in Wikidata, like all these different pages are connected to each other across many different languages. We basically looked at the potential answers that exist in our data set, and we translated them into many different languages. And then we extracted the Wikidata pages for all those different languages that correspond to a potential answer. But this gives us the whole article. We like to have the specific passages that contain the answer, okay? For that, we use our train generator to find which of those passages are in fact including the answer to the question. And we kind of use this step multiple times, find out the passages in different languages and cross-reference them with the question. This is our automatic labeling step, and then we iterate these steps by now we have a better DPR, kind of including more languages. We use it to train better generator and vice versa. Okay, so I removed a lot of details here. I refer you to look at the paper, but here are our results. The results are really good. On XOR QA that we used for training, and like for all languages on average, we see a lot of boost. Again, the dark blue is our system that combines MDPR and our MGen system, and light blue is kind of tries to does not uses our DPR system, it just uses simple kind of retrieval and then translation steps. And as you see in languages that are very low resource, our improvements are even higher, like in Telugu. Another interesting observation was when we took this our Cora, which is our multilingual QA system, and evaluated on MKQA dataset where we hadn't seen it for training. Again, we see big improvements across all languages. And again, in languages like Malay, our improvements are much higher when it is low resource. So I'm not listing all the languages, but we are getting really good results in 26 languages. But overall, as you see, like the absolute numbers are still low. So I'm kind of I'm inviting the community to actually work on this important problem that, okay, we have made a lot of progress in English QA, but how about in other languages? Okay. So far, I've described two of our methods for building general purpose models that work well across known tasks. Now, I like to change the topic to talk about when annotated data is scarce, right? And we like to build neurosymbolic models to be able to do complex reasoning, and we like to include external knowledge to guide the reasoning. In particular, I will describe two of our recent work. One is to elicit knowledge from structured data to guide reasoning to answer complex fact-based questions. And the second approach is to elicit knowledge from unstructured text, in particular from the parameters of the language model and show how we can make improvements in common sense reasoning. Okay, let me first define the problem of what I'm talking about when I say complex question. When was the football club founded in which Walter Otto Davis played at center forward? In order to answer this question, the system first needs to know what is that team that this particular player plays in, and then find the date where that team was founded, okay? This is a kind of open retrieval question answering. Again, we will have this pipeline of retrieving a few passages and then reading them. But there are some passages that are hard to retrieve. Why? Because at the first glance, it's not obvious how they are linked to this to this initial question, right? In particular, we need to retrieve the passage relating to this team, but now we only have information about the player. But the observation that we've made is these hard to retrieve pages are actually connected over a structured knowledge graph, in particular Wikidata or Wikipedia. And this is how our system works. We use a structured knowledge to guide the retrieval. We learn to retrieve reasoning paths and train a retriever-reader framework, and we show we get the state-of-the-art results. In particular, we first constructed the Wikipedia graph, how we basically connected the pages according to the hyperlinks that exist between these different pages. And we start retrieving paragraphs or passages sequentially by finding the reasoning paths over the Wikipedia graph. Or basically, let's assume this is our Wikipedia graph, then our reasoning paths are one path in this graph. And we train a recurrent neural network to actually start retrieving passages one by one from this Wikipedia graph. So again, don't go into the details, please refer to the paper. Now here is the overall approach. The question comes in. We train our RNN module to retrieve different reasoning paths. Now we've collected top K reasoning paths. We are not sure still which one contains the answer. We try to find the answer, the potential answer, according to each of these reasoning paths that are retrieved, and then finally re-rank them, see which one has the highest answer. Again, the results are really good. We achieved the state of the art in 3 data sets: Hotpot QA, Squad Open, and Natural Open questions. This paper is, I would say it's old. It's like almost 2 years old. And I know the numbers have improved a lot since then. So we showed here that the structured knowledge is actually really helpful in answering factoid questions. But now let's focus and ask this question when we are dealing with questions that require more implicit reasoning. Let's look at this question. This question is taken from Reno Grande dataset. I picked up a bag of peanuts and raisins for a snack. I wanted a sweeter snack, so I ate the blank for now. The way humans would answer such question is to start contrasting between the options that they are provided, or so-called facts and foils. We would argue that peanuts are salty while raisins tend to be sweet. That's why we would choose raisins here, because we were looking for a sweeter snack. But can we enable AI models to actually be able to contrast between facts and foils this way? The goal that we have here is to elicit this knowledge from language models through prompting, where we want to kind of extract this targeted knowledge by providing right interface to these language models. And we want to probe the knowledge that are contained in the parameters of this language model. How do we prompt these language models? We kind of are building some templates, like P are more blank than Q, P have blank while Q have blank, and so on. So we are forming these closed style patterns. And then we ask our language models to actually fill in those blanks, where hopefully they would provide us some attributes of those facts and foils that we are excited about to answer the question. So here is our full pipeline is built. We have developed zero-shot models for contrastive reasoning. First, we designed these contrastive prompts. We obtained these prompts from a small scale in-house kind of annotation with a few examples. In particular, we annotated about 100 examples, and we came up with about 20 of these type of patterns, like P are more blank than Q, P have something while Q have something else. And then using these patterns, we start prompting the language models, and then we let the language model to fill in those blanks, okay? So for example, they would have peanuts are salty while raisins are sweet. Peanuts have salt while raisins have sugar. Some of them are correct, some of them are wrong, obviously. And then we use these contrastive explanation in conjunction or concatenate them with the original question, and then train a task model if we are looking at fully supervised setting, or zero shot where we just look at the language model score to see which of those answers or which of those explanations are more likely. Again, the results are good. The dark blue shows the performance of our kind of contrastive based explanation. In 4 data sets, Vinogrande, different version of Vinograd, and also the PICA, which is asking about the physical kind of common sense questions. And we compare it with a model like the lightest blue, which does not use any explanation, or a little darker blue, which tries to provide explanation, but explanations are unguided. And we argue that this way of contrastive explanations, in fact, shows improvement in this domain. Okay, so I think I'm out of time, so I won't go into the last topic. I just wanted to introduce our newest data set. We call it natural instructions, where the goal is to be able to kind of build the capability of cross-task generalization. And here's the summary of the talk. I introduced general purpose models for question answering. I proposed the 2 neurosymbolic approaches that start to elicit knowledge from structured data or language models. And finally, hopefully we can make models that are able to generalize across tasks without seeing a lot of instances given a domain. Okay, thank you.
Thank you, Helen. Yeah, this is a very interesting talk.
Thank you.
So we have time for a couple of questions. Yeah, you can also read the question from the screen here. Yeah. So the first question is, can you comment how much does the training on multiple question answering data sets improve over the original T5 model? I think this
yes.
refers to
sorry. Yes, the last results that I was showing, then we fine-tuned unified QA. Actually, the comparison was with T5 fine-tune, like we basically compared with the exact same size model of T5 and unified QA. And in most of the data sets, we've seen boosts. I don't remember the absolute numbers, but definitely please refer to the table, to the paper to see the result. But yes, we saw the boost. And interestingly, that was there were next few works after this work, like for example, doing the same experiments in combining many different common sense data sets, observing the same impact and so on.
Great, thanks. Let's see, the next question is, why do you think text-to-text models such as T5 are good at extractive question answering problems? Do you think text-to-text models should be the basis of all the question answering models in the future?
Yeah, very great question. So I think currently text-to-text models are doing really well in question answering, especially because we kind of, so remember, these pre-trained models are trained with some sort of language modeling objective, right? Predicting what's come next, like in a very simplistic format explanation. But when we were thinking about like question answering or kind of some of these tasks that we have defined in NLP, the formats are really different, right? From the original way that these language models are trained. So if we manage to kind of make the input format of different tasks more aligned with the way that they are pre-trained, we have seen better gains, right? So I believe if these language models keep to be trained this way, I think it is very helpful if we kind of change the formats of our inputs such that they are aligned better with these language model training. But if we manage to come up with better pre-training objectives, then that's a different story, yes. And I know different people are working on that, like basically start pre-training more task specific. That's why I was thinking like, okay, it's really good to have something in between of the pre-training and fine-tuning steps. So we are kind of adjusting the model to learn different input types.
Great, thanks. Okay, so we have a question from Villain. So even seemingly small data sets actually require a lot of space and compute power to retrieve within reasonable time and are difficult to quickly experiment with because of their size. So in what ways would it be possible to make this approach more efficient, such as reducing retrieval time and the storage requirements?
Yeah, this is actually a very good question. So we have done some approaches on how to make the question answering more efficient, including like my work or Danchi's work of being able to do this maximum inner product search. But I agree, but again, it requires a lot of storage space and so on to make this more efficient. So we have had so this is an absolutely important problem. I don't think a lot of people have focused on that, or people in the information retrieval community are not as much in NLP. So we have basically borrowed one idea from information retrieval community of hashing these dense passage retrievals into kind of binary bits rather than kind of all these real representation. And then the storage space and retrieval efficiency improved by a lot without losing accuracy. So I believe it's really good to, again, kind of merge research efforts with information retrieval community, because it's kind of a well-known problem in IR for a long time, to kind of expand it for our type of retrieval in the NLP domain.
Great, thanks. Okay, so we have one more question from Hui Han. So does the language of the question or passage affect the value of the inner product? For example, do you find questions and passages in the same language have a higher inner product than if the languages are different, even when the meanings are the same?
A very good question. Yes and no. The languages that we have more resources for them, like we try to visualize the embeddings that we achieve for our Cora project. Yes, like we could see some clusters of tokens within language, but there were some languages that they were super low resource, that we saw that they were kind of very far from the everything else. So I think that is the important challenge, how to bring in those low resource languages into the same embedding space of the data. And yes, I definitely agree. It's also important to revise thinking about how we do language embedding such that, I mean, we need both objectives. We need the tokens that are within the same language be close to each other. Meanwhile, the tokens that mean same things across different languages be close to each other. So this is happening, but we are still seeing a lot of ambiguities. Yes, especially when we are talking about low resource settings.
Okay, maybe we can finish the last question. So the question is, do explanations also help in the few short fine-tuning regime?
Yes. The contrastive explanation results that I showed was actually helping more in the kind of, oh, you mean few shot and fine tune? Oh, very good question. Yes, we haven't tried in few shot, I don't know, but it helped in fine tuning regime as well. So we have results in the paper as well. Yes, it helped.
Great, thanks. Thank you so much, Hannah, for your great talk and the discussion. So we still have time, like on gather time, if people want to interact and ask more questions to Hannah. Thank you for coming.
Thanks a lot. Thanks for the invite.
Okay, so the next we are going to have our final spotlight session. So we are going to have 8 videos for the posters that will be presented later today. And then we also have the 3 outstanding paper poster sessions later today as well. Okay, Samir, could you?
Hi, my name is Bill Hogan. I'll be walking through our recent work titled Abstractified Multi-Instance Learning for Biomedical Relation Extraction. The question we're asking is, how can we automatically extract fact triples from large amounts of raw biomedical text, such as PubMed? In this work, we use a distance supervision approach where we start with a knowledge graph of biomedical entities and raw text from PubMed. Then we make the assumption that any sentence that contains an entity pair that is linked in the knowledge graph expresses the relationship between those entities. This allows us to automatically generate labels. However, this assumption leads to very noisy labels since not all sentences will express a relationship. To address this issue, the current state-of-the-art models use multi-instance learning, which groups sentences into bags with the intuition that a group of sentences will more likely express a relationship than a single sentence. However, fact triples and their corresponding sentences suffer from a long-tail distribution. Over 50% of entity pairs are only supported by 1 to 2 sentences, and in such cases, we heavily rely on upsampling to fill bags of sentences, which diminishes the effectiveness of multi-instance learning. To address this issue, we developed a model that adds a layer of abstraction. We call it abstractified multi-instance learning. We abstract entities into their corresponding entity type and use the entity types to form bags of sentences. Using this method, we were able to reduce single sentence bags by half. Relationship embeddings were also improved with our model by conducting a suite of relationship embedding experiments, and we propose a few novel relationship representations that improve model performance in all metrics. Here we see an example of data flow in our model AMIL. We start with a bag of sentences, send it through BERT, get the encoded input sequence. We concatenate selected tokens to form the relationship embedding and send it through a linear layer, which predicts the corresponding relationship type. Looking at the performance, we see here that AMIL beats the current state-of-the-art in almost all metrics, and our novel relationship embedding type L here ends up improving again on top of our AMIL baseline. For more details, check out our paper, and thanks a lot.
Hello everyone, this is Kuntal Pal, PhD student from Arizona State University. I'll present our work, Common Sense Reasoning with Implicit Knowledge in Natural Language. In this work, we use 3 existing common sense reasoning datasets, abductive NLI, physical IQA, and social IQA, to study how well can the transformer encoders like BERT and Robota perform common sense reasoning with implicit knowledge in natural language form. First, we find out respective relevant knowledge sources for each of the datasets. Then we filter out 10 knowledge sentences using IR and knowledge ranking strategies. The top 10 knowledge sentences retrieved from each of the options are infused with the transformer encoders in 4 different ways. We have 4 models: concat, parallel max, simple sum, weighted sum. We use 3 training strategies. In the revision strategy, we first pre-train the model with the knowledge sources and then fine-tune on the datasets. In the open book strategies, we only fine-tune the models on the datasets along with the extracted knowledge. The final strategy is a combination of both. In this sample of PICA dataset, we show that how our weighted sum model works. Results, we find the revision with open book strategies along with the weighted sum model works best. Here we show how our weighted sum model compare with other existing models. We randomly picked 200 samples from each of the datasets and analyzed the performance. We show the impact of number of knowledge sentences on weighted sum model. We also probe the weighted layer of the weighted sum model to interpret why it performed better than other strategies. Finally, to conclude, we performed a thorough analysis of transformers' ability to reason, introduce 4 knowledge infusion modes, and carry out extensive investigations about impact of knowledge. Thank you for listening. If you have any question, please feel free to contact us.
Everyone, my name is Simon Ott from the Medical University of Vienna, and I'm introducing you to Saffron, an interpretable rule-based link prediction method outperforming embedding models. Recently, a highly efficient rule learner called AnyBurl has shown very promising results in the field of link prediction. What makes rule-based approaches preferable is that they yield an explanation in terms of the rules that trigger a prediction. However, despite these advantages, the application of learned rules currently has limitations. First, functional redundant rules make it difficult to aggregate predictions made by the different rules. And second, due to scalability issues, the application to large-scale knowledge bases is limited. To solve these issues, we created Saffron, a framework for applying symbolic rules and meaningfully aggregating their predictions. It tackles the problem of redundant rules by implementing an algorithm which clusters such rules and makes meaningful predictions even if the rule set contains redundant rules. Furthermore, Saffron was heavily optimized to enable the application to large-scale knowledge bases. We applied Saffron to 3 well-known benchmark datasets where it could achieve new state-of-the-art results for fully interpretable link prediction and exceed the results of multiple established embedding-based algorithms. Thank you.
Hi everyone, my name is Shadi Halou. I am a PhD student at the Institut Polytechnique de Paris. Today, I am presenting a preview of my poster, Reasoning with Transform-Based Models, Deep Learning by Shallow Reasoning. Recently, transform-based models are performing very well on many NLP tasks. However, do they really understand natural language? The survey paper discusses the performance of transform-based models on different reasoning tasks. I will briefly outline some common pitfalls that any transform-based models need to handle in order to reason on natural language. These pitfalls are negation, being sensitive to mispriming, memorizing pattern heuristics, and being insensitive to word order. One major question to ask is if transform-based models have deep reasoning capabilities. Short answer, no. The strength of transform-based models is that they can learn simple patterns combined with background knowledge from pre-training. The tasks that can be easily solved are horn rule reasoning. It is when the facts and rules are explicitly shown to the model, simple common sense reasoning, and simple mathematical reasoning such as asking a model to add 2 numbers. However, they fail on other reasoning tasks such as implicit reasoning, is when the facts and rules are not explicitly shown to the model, and visual common sense reasoning, and mathematical word problems. Our last question is if there is any task that transform-based model cannot solve even if trained on a large dataset. Short answer, yes. Transform-based models have theoretical limitations that fail to model the even parity and Dike-2 languages. Even parity is a set of bit strings where the number of ones is even. Dike-2 is a language of strings that are a balanced sequence of round brackets and square brackets. In order to see how these impact natural language, we designed 2 natural tasks, the light switch task and the cake task. The light switch task is assuming that the light is off in the beginning. The goal is to determine whether the light is on in the end. The goal of the cake task is to determine whether a sequence of steps is possible and if the cake is gone. We confirm that this limitation have an impact on natural language. Thank you.
Hello everyone. Today we are going to present our paper Relation Prediction as an Auxiliary Training Objective for Improving Multi-Relational Graph Representations. This is a joint work between UCL NLP and the Facebook AI Research London. We focus on the task of knowledge-based completion, where we want to predict missing edges given present edges in the knowledge graph. For example, in this figure, we may want to predict whether Maurice Depton is the award winner of Academic Award for Best Supporting Actress. In the past 10 years, many models have been proposed for this task. On the other hand, there are some recent work that point out under a sensible evaluation protocol and with appropriate training strategies, simple models can perform in a very competitive way. Inspired by this, our work proposes a new self-supervised training objective by simply incorporating relation prediction into the commonly used one versus all objective. Formally, our objective is shown as this equation, where lambda is a hyperparameter balancing the entity prediction and the relation prediction. Consistent performance improvement can be observed across datasets. Our ablation study also shows that relation prediction helps particularly at larger embedding sizes and on datasets with unknown relation types. In the future, we are going to extend this objective to more complex models and more downstream applications besides link prediction. Thank you.
Hi, today I'll present analyzing common sense emergence in few-sought knowledge models. To begin, I'll give an overview of the task of common sense KG generation. Given a head entity in a relation, we ask models to predict tails generated from the LM. For example, for the head person X opens the fridge and relation X1, some potentially valid tails could be to get something to eat or to get something to drink. Traditionally, common sense knowledge models were trained on fully supervised settings, which needed tons of examples across the entire KG. Recent work shows that we can use templates to extract knowledge directly from pre-trained LMs. But these generations produced are generally low quality compared to fully supervised options. We propose using these same templates for few-sought adaptation, allowing us to create few-sought LMs quickly with low data with quality ratings that near that of fully supervised options. We also investigated how the parameters of these models change over the course of few-sought fine-tuning to provide insights into how common sense representation capabilities emerge in these models. Next, we'll go over some of the most interesting results. We find that large LMs use more specialized parameter matrices during learning, suggesting that they are able to produce higher accuracy generations by using knowledge stored in the parameter matrices. We also find that large LMs experience less destructive interference during training, further suggesting reasons for their ability to learn knowledge faster. Finally, we find that while variations between prompts are not important, prompts do need to accurately describe the relation to produce high quality knowledge learning in the few-sought setting. Thank you for listening, and we provide code and paper results in this link.
Hello everyone, in this video, I would like to talk about our work on knowledge extraction from long fictional texts. Relation extraction from web contents is a key task for the automatic construction of knowledge bases. However, current KBs are mostly extracted from mainstream texts in real-world domains and lack knowledge about long-tail domains, where fiction and fantasy are archetypes of them. While input of knowledge extraction in real-world domain mostly comes from Wikipedia pages and news articles, input for fictional domains comes from books and fan-built content. Work on KB construction in real-world domain has mostly focused on general-purpose encyclopedic knowledge of prominent people, place, etc. with basic relation of wide interest such as birthplaces and spouses. In fictional domains, on the other hand, getting more interested in narrative fiction knowledge that related to prominent characters, places with relations that captured traits of characters and key elements of the narration such as allies, enemies, skills, and so on. There are two main challenges when working on knowledge extraction in fictional domains, which are lacking of training data for non-standard relations and working on very long input texts, such as entire books. To overcome these challenges, we proposed a method called NoFi. Our method leverages semi-structured content in wikis of fan communities to extract background knowledge for 142 popular fictional domains. This serves to identify interesting relations and to collect distance supervision samples. Yet for many relations this results in very few seeds. To overcome this sparseness challenge and to generalize the training across the wide variety of relations, we devise a similarity-based ranking technique for matching seeds in text passages. Given a long input text, NoFi judiciously selects a number of context passages containing seed pairs of entities. To infer if a certain relation holds between two entities, NoFi's neural network is trained jointly for all relations as a multi-label classifier. Extensive experiments with long books on 5 different fictional domains show that NoFi clearly outperforms state-of-the-art RE methods. We also introduce Lawfido corpus for relation extraction in long fictional documents. More details can be found at the link below. Thank you for your attention.
Thanks for watching the presentation of our work, Ambiguous Quokka, clarifying ambiguity in conversational question answering. In conversations, a question is considered as ambiguous if open to more than one interpretation. For example, here shows a conversation about a story. The question QI, what color was it, is ambiguous because according to the story, the mother found 2 books in different colors. For machines to engage in an effective communication, the ability to identify ambiguity and request clarification are required. However, few studies have explored it. With this purpose, we introduced a novel crowdsourced dataset, ambiguous COCA. We collected human annotations on the following 3 tasks. We first detect whether QI is ambiguous or not. If ambiguous, then generate a question for clarifying the ambiguity, and answer QI based on each possible clarification reply. To summarize, first, ambiguous COCA is in a reasonable size for training models. It consists of 4,000 passages and 8.6 thousand conversational questions, where 1,000 of them are ambiguous. Second, our dataset is diverse with respect to the clarification strategy, the ambiguity type, and the source domain. Third, our proposed tasks are challenging. We evaluate strong language generation models such as BART, GPT-2, and conversational question answering models built upon BERT and XLNet on our dataset. The best performing systems are largely behind human performance, indicating there is ample room for improvement. We demonstrate the limitations of these end-to-end models and discuss possible future work. Please read our paper for more detail. Thank you.
All right. So this concludes our spotlight session. So next, we encourage people to move to the other room called posters and chats. And our speakers team and Hannah will be there for interactions and taking more questions. And our next invited talk will start at 11 a.m. Pacific time. So we'll see you soon on GatherTown.
Okay, hi, welcome back, and welcome to the last session of the main conference. We have two great invited talks, and followed by the closing remarks. So it's a pleasure for me to introduce Daphna Shachaf. Daphna is an associate professor of computer science at the Hebrew University, and her research focuses on helping people make sense of massive amounts of data, with an emphasis on unlocking the potential of digital traces left by human activity to contribute to our understanding of human capacities such as humor and creativity, which is not surprising since her own research is so creative. She received her PhD from CMU, was a postdoc at Stanford. I was there too at the time, and at Microsoft Research. She has won numerous awards, including Best Paper Awards at KDD twice, an ERC grant, Microsoft Research Fellowship, a CBO scholarship, and many, many more. So it's really a pleasure for me to welcome Daphna to AKBC and listen to what she has to tell us today.
Thanks, Jonathan. Okay, you can hear me, see my slides, everything is according to plan? Okay, good. So hi, everybody. I'm Daphna, and today I'm going to be talking about accelerating innovations for analogy mining, which is joint work with many people, but in particular with my ex-student, Tom Hope, who might be in the audience. He just got outstanding paper here a couple of hours ago. So hey, Tom, congrats. Okay, so let's start with this guy. This is Thomas Edison, also known as America's greatest inventor. He's responsible for many inventions that you have heard of, like the phonograph, the motion picture camera, and the practical light bulb. And the reason I had to explicitly say practical here is that while I was looking up stuff about Edison, I realized the internet has gone completely insane over the question of who should get the credit for the light bulb invention, whether it's Edison or Tesla. And when I say completely insane, I'm not joking, okay? You can get a t-shirt supporting your favorite inventor. But with or without light bulb, Edison is still a genius inventor, and I recently stumbled upon an interview held with him where he talks about what makes somebody a great inventor. So Edison said that in working out an invention, the most important quality of an inventor is, take a couple of seconds and try to guess it, just because it's fun. The most important quality of an inventor is plenty of money to throw away. The second most important quality, according to Edison, is, well, this is a bit more vanilla, it's imagination, because you need to imagine something that doesn't exist yet. But what really got to me is the third thing he said. And he said that the third essential is a logical mind that sees analogies. Now, the next paragraph is just too good, so I have to share it with you. Okay, bear with me for a second. He says a logical mind that sees analogies, and then he immediately goes on to saying, no, not mathematical. No man of a mathematical habit has ever invented anything that amounted to much. And he continues to say that he himself doesn't know anything about math, can't even do proportions, but he can hire all the good mathematicians he needs for $15 a week. Okay, but go back, so a logical mind that sees analogies. And he has a point, because throughout history, analogies have been a driving force of innovation, where you have ideas from one domain that are used to solve a problem in another. The ancient Greeks looked at water waves to understand the sound phenomena. Salvador Luria got a Nobel Prize when he saw an analogy between slot machines and bacterial mutation. NASA hires origami experts to help them develop a folding spacecraft, which is super cool. You should go check out the video. And perhaps my favorite example is, my recent example, I have something called the Odon device. This is a super cheap device used to help babies that are stuck in the birth canal. And the great thing about this was invented by a car mechanic after watching a YouTube video with a party trick, how to extract a cork from a wine bottle. And the thing is, this invention has the potential to save millions of lives. The World Health Organization said that this is the most innovative thing that has happened in this field in maybe centuries. And all of this because this guy watched a YouTube video. So my point is that the web is full of potential inspiration sources. We have almost 10 million patents just out there. We have scientific publications. We have crowdsourced innovation websites like Kickstarter. And all of this is really an unprecedented opportunity to find analogies. Having said that, it's also a major cognitive bottleneck, because you can't expect anybody to be familiar with 9 million patents. So the natural question is, can computers help us find analogies? Okay, so the goal or the grand vision of this project is to design a novel system that can automatically discover analogies in such large, messy, unstructured natural language datasets. And if today analogy finding relies mostly on serendipity, kind of the lone inventor sitting in the attic, I want to turn it into a reliable on-demand process that can scale to find inspiration among millions of ideas. Okay, this is kind of the grand vision. You with me? It's frustrating not to see the audience. It doesn't even have like the Zoom, the squares. Okay, I'll pretend you're nodding. Okay, so here's the bad news. Analogies have been a holy grail of AI for quite some time. Douglas Hofstadter wrote an entire book arguing that analogy making is at the core mechanism of our thinking. Okay, he said that it's the central mechanism upon which all human thinking rests. Yet AI is not really close to realizing this. And if you try to think about why, like what's the obstacle, it seems like one of the biggest challenges is that the computer needs to recognize that two things are similar, despite the fact that they use very different words to describe them. For example, none of today's NLP methods will tell you that babies are anything like corks, but Odin realized there was something interesting in their relations there. Okay, so let me give you a bit of the history of computation analogy. For a really long time, this field relied on handcrafted datasets with high relational structure. Think about the seminal work of SME. I think I saw Ken Forbes here the other day, so maybe he's still here. This is what it would look like, roughly, for the extracting a cork from a wine bottle. So you see enable. If the uninflated plastic bag is smaller than the bottle opening and the person inserts the plastic bag into the bottle, so on and so on. And at the end, you have cause. If the person pulls the plastic bag, it causes the cork finally not to be in the bottle. So as you can see, this is super difficult to obtain and most often does not scale. I cannot get annotators to do this for 9 million patents. So the first thing we said was say, okay, so let's do what we know how to do, which is machine learning. And we got data from this website called quirky.com. You probably haven't heard of it. Think about it as Kickstarter's little brother. Okay, it's a crowdsourced innovation site. And we crawled 10,000 product ideas across different categories because we want those cross-domain analogies. Ideas are in natural language, usually so-so English. Here's an example text just so you see what we're playing with. So this is a text about an invention that helps your pet drink while driving, drink while you're driving. So the first thing we said was, let's just treat it as vanilla supervised learning, which means I need to have positive examples and negative examples, right? I need to have examples of pairs of products that are analogous and pairs of products that are not analogous. So what we did, we built a search engine on top of those 10,000 quirky products, and we gave crowd workers this seed document, like headphones that can control Pandora or Spotify. And we told them, you have a search engine, find other products that are analogous. And we explain what we mean by analogous. And they could scroll through the list and search terms and mark things as analogous. Now, positive examples is pretty straightforward, whatever they marked. Negative is a bit more tricky. This was implicit, stuff that they have looked at, but chose not to mark. Okay, and there's a reason I'm going through this at 100 miles per hour. We threw on top of it deep learning, of course, a Siamese net with contrastive loss. The idea was to learn a similarity function, a metric function, distance function. If two things are close together if they're analogous, far apart if they're not. What we did, we took all the pairs of documents in our test set, we ranked them according to this distance that the network learned. And if you look at the top 2% of the ranking, we had 64% positives, while just random would give us something like 11%, which at first glance seemed super promising. And yet we decided to completely abandon this direction. And let me tell you why. So first of all, the labels were super slow and costly to get. But this is okay, this I can live with. But they're also really, really noisy. So there's lots of work in cognitive psychology telling you that people tend to gravitate towards superficial matches, things that match on feature level. This is headphones, this is also headphones, they must be analogous. This is exactly what we saw in the data. Okay, so the algorithm managed to mimic what people were doing. People just were not doing what I wanted them to do. Also, it seems like just using the text as is means that the model is really blind to all those rich structures in there. So we went back to the drawing board. And what we said was that you can think of it as a spectrum. And on one hand, you have those logic-based representations. that are super hard to get, but if you have them, finding analogies is relatively straightforward. And on the other hand, you have raw text, which is practically free, but it doesn't really get us much closer to be able to finding analogies. So the question was, can we find some sweet spot in the middle, some representation that's expressive enough to help us find analogies, but easy enough we can learn to extract it from raw text? Okay, good. So we landed on this idea from cognitive psychology called schema induction. And in a nutshell, this means that if we can take this text describing a product and extract two things, what is the purpose of this product, what's the goal, and what is the mechanism, meaning how it achieves the purpose, then we can solve some core analogic task. For example, find me another product with a similar purpose, but totally different mechanism. Or the other way around, find me another product that uses a similar mechanism to solve a completely different problem. So this means we actually had to take those texts and try to extract some representation that's the purpose and some representation for the mechanism. Okay, we went to Mechanical Turk. I basically live by Mechanical Turk. And we showed them some products and asked them to mark spans of text. First of all, how does the product work? And what is it good for? So on the left, you see, okay, this is the amazing pillow product. So how does it work? They mark components. It has a pillow, alarm clock, Bluetooth, sensors, LED lights, blindfold, whatever. And what is it good for? They mark spans like improve and monitor sleep, wake up comfortably, track sleep patterns, full support for any kind of sleeper, and for comfort. Okay, and in this work, I'm going to talk about extensions soon after, but in this work, we were interested in capturing just the overall purpose and mechanism representation. So I'm not trying to predict any individual words. So what we did was taking glove embeddings of those words, weigh them by TF-IDF across the workers, and this was our target vector. This is what we were trying to learn for purpose and then for mechanism. And this was 2017, so we used a bidirectional GRU RNN that tries to predict both the purpose and the mechanism. Let me jump to the part I'm most excited by. So I spent 2 minutes in the beginning of this presentation telling you that analogy is amazing for getting people to be more creative, for driving innovation. So what we did, we decided to test this in an ideation task. We gave people some seed product. For example, here you see a cell phone charger case. It's a cell phone case that has a secondary battery in it. So it increases the life of your battery. And we tell them your task is to find other ways to solve the same problem, meaning to extend your battery life. And there are 3 conditions in this experiment. First of all, random products from Quirky, because there's lots of studies about how random is supposed to get you to be more creative. Standard search, and ours, meaning finding other products with a similar purpose vector, but diversified mechanism vector. And the idea of the study was that random is going to be super diverse, but completely irrelevant to the problem. Surface similarity, the search engine, standard search is going to be super relevant, but also very focused, very narrow. Everything is going to be about cell phones. And ours is hopefully going to be diverse, but still relevant to the problem, which will allow the user to explore some parts of the design space they wouldn't have thought of exploring. Okay, so let me show you some actual snippets from the inspirations we showed people. So on the right, you see random with stuff like the dog meetup app, because that's what the world really needs. Middle is surface similarity. So you see multi-adapter case, cell phone battery with GPS, cell phone case with GPS. So like we said, very narrow, very focused. And on the left, you see our approach with a flash charge carabiner, USB tower with backup battery, and this crazy thing. I love this thing. It's basically a suit full of pulleys. So when you walk, it generates an emotion energy. Does not mention cell phones. I'm not even sure it mentions battery, but it's clearly about this concept of generating energy. So people have seen inspirations according to their conditions, and they generated a long list of ideas. I just want to show the first one in blue. This is somebody exposed to our inspirations. And the first thing they write is a case that tracks steps and generates power using your movement. Now, I don't know if it's because they saw the suit with the pulley or not, but I can basically hope so. Next thing we did, we took all this long list of ideas and we had them externally rated by 5 judges according to criteria that are standard in creativity research. So there's novelty, meaning you're solving the problem in a new way. Quality, meaning you're solving the right problem. And feasibility, meaning you're not breaking physics. There's no time travel or cold fusion involved. And the bottom line was that no matter how you slice and dice it, if you look at the proportion of good ideas or the absolute number of good ideas, people who were exposed to our inspirations got a really nice boost to their creative ability. So at this point, everything was amazing. We wrote this, we sent it to KDD, we got best paper. But I think most importantly, to me, this was the first proof of concept that this idea of purpose and mechanism actually has merit, that we can continue exploring this direction and it has potential to make progress. So you can think of it as the first step that my lab took towards this rabbit hole of analogies. And in the time I have left for this talk, I'm going to tell you about some of the extensions we've been playing with since this base work. Okay, I'm going to tell you about 3 extensions where we try to extract more useful structure from the text, meaning to push ourselves farther down this spectrum to more structured representation. And 1 extension that's about common sense and expressive queries, more user-facing. Now, this part is going to be less technical, even than what I did so far. I'm mostly going to show you examples. There's going to be a little bit of cherry picking, but my goal for this part is to show you what can be done if you have this representation, if you can extract it reliably. Okay, good. So first thing we did, which was kind of selfish, frankly, we wanted to find analogies between research papers. So this was a pretty straightforward extension. We got a schema, and instead of just purpose and mechanism, we also identified the background and the findings of each paper. And again, my favorite part was evaluation, where we managed to find novel and useful analogies for a domain expert in mechanical engineering in areas that they would have never ever thought of looking at. Then we proceeded to biomimicry or bio-inspired design. So, this is the process where you have some engineering problem, you're looking for an inspiration in nature. This is one example that I really like. Speedo designed a swimming suit modeled after a shark skin. And now you're not allowed to swim with it in competitions, in the Olympics, basically anywhere, because they just broke all the records. So you can't do this anymore. So what we did in this project, we tried to augment our representation with QASRL, with semantic role labeling, to better understand the structure of the text. Okay, so if you have a sentence like this, we know that sharks have a covering of dermal denticles that is used for improving what? Fluid dynamics. Okay, so we get a better understanding of the purpose and the mechanism used to achieve it. And we built a prototype biomimicry search engine where you type stuff like protect eyes, and you get a list of animals that have coped with this problem and have their own mechanism for solving it. I'll just show you some because it's fun. So for protect eyes, you have, for example, sharks. Did you know that sharks can roll their eyes back into their skull when they attack, so to protect their eyes? And you have caracals that apparently have some complex structure of the eyelids used to protect their eyes. And this is my favorite example. It's this fish that has a transparent head, and its eyes are actually inside the head. But what you think of as the eyes here is actually not the eyes. The eyes are those green barrels that you see inside, which I think is a genius engineering solution for protecting your eyes, right? Just get them inside the head and make the head transparent. Okay, so this was biomimicry. The third extension, so if you remember in the KDD work, we had this representation of one aggregate vector for overall purpose, one aggregate vector for overall mechanism. But in reality, products have multiple purposes and multiple mechanisms. And this representation was kind of squishing them together. So it's more natural to look at this as a problem of sequence to sequence, right? Where what we really want to extract is spans of stacks corresponding to purposes and mechanisms. And this will allow us to disentangle different facets of the product. So if you go back to our mechanical Turk annotations, you can still use the same annotations, but now we train the network to actually predict those spans, okay, to extract those spans. Okay, so what I really want to show you is what you can do once you can extract those spans reliably. And we have 2 use cases. The first is expressive queries. Okay, suppose you're a company manufacturing light bulbs, and you know all the standard things you can do, right? You can make flashlights, you can make lamps, but you really want to identify some non-standard uses to be able to expand to new markets. So using our search engine, relying on those purpose and mechanism spans, you can construct a query that looks like this. So the purpose is not light, and the mechanism is light. Okay, so you want something that the purpose is not light, but uses this mechanism still. And I wanted to take a second and think about how you would pose this query in a standard search engine, say in Google Patents. It's really tricky to pose this specific one. Okay, let me show you our top 3 results of the search engine. So a billiard laser guide, which I did not know was a thing, but now I desperately want this for my birthday. Warning signs on food, for example, for kids with allergies. And like those small lights you put on furniture so you don't stab your pinky toe on them in the middle of the night. And again, if you think about it as this use case of a company that wants to expand to new markets, those are good ideas for them. The second use case, exploring the design space, this one I'm even more excited by. The idea here is that if you have a corpus of inventions and you can extract purposes and mechanisms, you can build a graph mapping the entire landscape of ideas. So what are all the problems that mankind has been facing? And frankly, what solutions have we found so far? And it can really help problem solvers break out of fixation. Let me show you how. So suppose you're an engineer and you want to design something that can wash cloths without water. You're in the desert, you're in space, you're somewhere where water is scarce, whatever. So what we do, we construct a graph. We cluster together purposes and we cluster together mechanisms based on semantic similarity. So the most obvious thing you can do is, first of all, look for the purpose cluster that's closer to the purpose you have in mind, for example, this one. And then you can go through the documents associated with it and filter them according to the mechanism. So looking just at ones that have mechanism that is not with water. Okay, so you might find something like this, a waterless washing machine that scrubs clothes clean with dry ice. But what I think is a more interesting way to use this graph is to explore neighboring clusters, which is really a way to reformulate the problem you have in mind. So like, wait a second, maybe you don't really care about washing clothes, maybe you just care about removing bad odor. Then you might come up with an idea that's more like a deodorizer. Or maybe you want to look at how people clean stuff without water, but not necessarily clothes, just other stuff. And you'll look at stuff like dry shampoo. So my point is that exploring the neighborhood can really expand the innovator's conception of the problem space. And also, and that's important, help them identify the underlying, even implicit assumptions that they're making and see if you can actually break those assumptions. For example, see this very last cluster at the bottom? It has stuff like biodegradable yarn, which causes you to stop and think, wait a second. So I had this assumption that you have cloths and they need to be cleaned and reworn. But what if I can just use them once and they're going to disintegrate? So my problem is really just get myself a big enough stack for however long I'm away from water, right? And I'm going to use them once and they're going to disintegrate. So it's a really fun way to kind of rethink about the problem. We ran a quick preliminary ideation study. Again, we showed people problem and inspirations that were either from our graph or from baselines. We had 62% of the inspirations found useful, which is actually more than I expected. Best baseline was a bit under 40%. And again, I'm just going to show you one cherry-picked example, but really cute one. So this person had the problem of folding laundry, and they got the inspiration from our graph about storing toilet paper. And they came up with this idea of why fold laundry when you can roll laundry, which is apparently something that people have been doing. I was not aware of this, but I don't know. I think it's a really cute solution. Okay, so those were the 3 about structure, and I promised you one more that's more user-facing, about expressive queries. So this one actually, we started this one when we conducted experiments with a prototype of the analogy search engine. We had designers show up with their own problem, okay, not some problem we gave them in an ideation study, and we just asked them to play with the engine and see what comes out. And one thing we immediately learned that really surprised me in real time, that makes a lot of sense in hindsight, is that people really wanted to get a better control to guide abstractions. Okay, analogy is really about abstractions, right? Some properties you want to keep, some properties you're okay with throwing away. And people really wanted to be able to tell me what's important for them. Maybe the best example is this person coming to us with a problem about stents. And we found an analogy which I thought was great about water and turbulence. And they just looked at it and say, well, great, but blood coagulates and water doesn't, so this is completely useless to me. Okay, which makes sense. So this got us to come up with this other system called focus abstraction. I'll demonstrate this on another quirky product. This one is a soapy slider. It's basically a fancy soap dish. So suppose you're a designer and you want to redesign this aspect of how it extends to different sizes of soap bars. So our system lets you click on words, and then you get a list of common sense properties. For example, what's really crucial for the analogy here? Does it matter that soap is a toiletry substance? What about chemical properties like it's a surfactant? How about that it's a cleaning substance or water soluble or slippery? Because I can imagine cases where it's crucial that it's slippery and cases like here when it's not. So in this case, we just pick personal product. Same thing for any other word like size. So if I show you analogies for stuff that's adjustable to different height or weight, are you going to be happy? In this case, I pick spatial quantity as the right level of abstraction. So the query is actually extendable. I'm looking for products that are extendable to different spatial quantity of some personal product. And here are the top two that we found: knife Rolodex that has multiple slots for different sizes of knives, and a phone, a kind of telescopic frame that adjusts to different sizes of phones and tablets, which are again good inspirations if you keep in mind this soapy dish designer that wants to extend to different sizes of soaps. We again had another experiment with designers. They're mostly able to express their needs, so we have decent coverage. It did help them identify more abstractions and finding analogies in distant domains. One more favorite example of mine, this person came to us with a problem of removing excess oil from French fries. We got an abstraction of separation of liquid event, and the system suggested hydrophobic coating. Now, I don't know about you, I probably do not want hydrophobic coating on my French fries, but this just got this person to think in a completely different angle. So instead of removing the oil after it's already there, I just make sure it doesn't get there in the first place. Okay, so what did we have here? Hopefully I convinced you that analogies are awesome and worth exploring. Why? Because analogy mining tools and series could hopefully revolutionize many fields. Okay, I have this vision of scientists, inventors, designers that find content based on deep structural similarity, not just simple keywords. As a personal holy grail, I also hope some of the stuff that we're doing will feed back into cognitive science to understand why people are sometimes bad and sometimes horrible at analogies. Why now? Because there's an explosion of data available online and tremendous progress in machine learning and NLP. I really don't need to preach to this crowd, but like I said, an unprecedented opportunity to finally tackle this problem. And what next? Well, my group is working on more complex representations on new domains like patterns and biomimicry, on human-computer issues, so how to get people to understand what's a good analogy and what's not. My old nemesis, common sense, which is huge here because lots of stuff doesn't even appear in the text. And if you have suggestions, well, you know where to find me. Thank you.
Okay, I'm back. Thank you. I learned a lot, as always, even about fish and stuff. So we have many questions, and they will appear magically. So I'll read them out loud, but you can see them as well. So you've described nicely how to find good analogies. What do you think could now be done on automating using those analogies to solve problems?
Okay, I love this question because when I started this project, I assumed that this was the trivial part, that if I just show somebody an analogy and they know the problem, this is called the adaptation phase. I thought that adaptation is super easy, but there's lots and lots of work in cognitive psychology telling you that people are really bad at this on both directions. So they don't recognize a good analogy when it's dancing in front of them. And the other way around, sometimes an analogy is broken and they still think it's a good one and they'll still use it. So now my group is actually working on identifying clues, kind of telling people, hey, we think this is an analogy and we think this maps to this and this maps to this. Here are the similarities, here are the differences. And we hope that this is going to make it easier for people to adapt the analogy to their problem. Like completely throwing people out of the loop, I don't think we're there yet. I would be happy to, but I don't know, not anytime soon as far as I'm concerned.
Cool. So I think the next question is the same. If you mind the analogy from the web, yeah, I think that's the same question. So let's skip to the next one. So do you think you can
Actually, don't think it's the same question, by the way. I think
You
they're
can
basically
answer
asking me
it,
if
so,
I'm,
like,
yeah.
Let's say, okay, so I will repeat it. If you find the analogy, isn't it already invented? So in some sense, why do you need it? It's already invented.
So I'm not finding the solution to your problem. I'm finding something that will inspire you. For example, okay, suppose you want to design a kindergarten chair, okay, that does not fall when you push it, something that's stable. And I give you kind of a, what do you call those dolls that you push and get back? Roly-poly, something like this. And you'll say, Whack-a-mole? No, that's a different game. I think it's called Roly-poly. Anyway, you know what I'm talking about, right? And then you say, oh, I'm going to design a chair that has kind of, a rounded bottom. So I push the chair and then it's going to get back up. So it's not like Roly-poly was already a solution to your problem. It was just an inspiration. Okay, go.
Cool. So do you think you can mine products with patterns like a startup idea and stuff from like social media?
Oh, I have not thought about this. How popular is this startup idea pattern? I'll need to look at what people actually publish there. Like, do people actually give startup ideas, or is it just like, making fun?
You can try Twitter. There's it's open source.
I'll check it out. Okay, cool. I haven't thought of this.
So we can still have time. So it seems purpose and mechanism are specific axes for analogy. Is there some taxonomy of what are the relevant axes? X is like Y because, I don't know.
Yeah, so there's a taxonomy of axes for analogy. So I guess that boils back to the first answer I gave. So now we have, okay, my ideal thing would be not just purpose and mechanism. My ideal thing would be more like the structural mapping engine, the kind of the logic-based representation I talked about, just automatically constructed. So here are all the moving parts in the source, here are all the moving parts in the target. And this is why I think that they're maps. Those are the relations that are kept between them. Purpose as mechanism is really like quick and dirty way to get at some of it. But by no means this is like the final solution. I don't want to say final solution, but this isn't the end of it. And we're thinking about more complex representations all the time.
Okay, I think we'll take, we can take more. So the next one, do you think there is hope for using huge language models? I assume GPT-3 like to get creative ideas. You can prompt them with, another way you can use a light bulb is,
I've actually tried it. Well, we just got access to GPT-3, so far I've been using all kinds of other ways to get there. Sometimes it's surprising good. Sometimes it fails horribly. But it's all prompt engineering. Maybe we haven't found the right way to do this. We have also tried doing extraction of mechanisms, extraction of purposes, doing abstractions. All I can say, this thing is powerful, but definitely not like the panacea yet.
Okay, I think we should probably stop. You will be around for more questions, probably in the chats with the speakers.
Mm-hmm.
And now for the final talk of this day and of the main conference, Danchi will take over once again.
All right, thanks, Jonathan. So next is my honor to introduce our next speaker, Greg Durrett. He's also the last speaker of our main conference today. So Greg is an assistant professor of computer science at UT Austin. He did his PhD at UC Berkeley in 2016 with Dan Klein. His current research focuses on making natural language processing systems more interpretable, controllable, and generalizable. And Greg has done a lot of interesting and influential work from the early days of information extraction, anti-linking, reference resolution, to more recently question answering, text reasoning, and summarization. So Greg always gives very interesting talks. And today he's going to tell us why natural language is the right vehicle for complex reasoning. And I'm very excited to hear this talk. Greg, please take it away.
Okay, thanks, Tenchi. Can you see the slides and everything? Everything looks good? Okay. Cool. Well, thanks for the nice introduction. And yeah, it's great to be here. So I guess a lot of this talk is not going to discuss sort of explicit knowledge bases, but I think it's going to echo a lot of the sentiment that we've heard throughout the week about moving more towards natural language representations of knowledge and what you can do with those. So I want to specifically focus on complex reasoning and why I think natural language is the right vehicle for expressing that. So let's start off with textual entailment. So we have an example here of a premise: a dog is chasing a cat, and two hypotheses. Two animals are running and two animals are sitting. So a pre-trained transformer model, this is the Roberta MNLI demo on Allen NLP, will correctly judge that the first is entailed and the second is contradicted. So I would argue that there's some kind of reasoning going on here. You can probe this model a little bit more thoroughly. You can try some different, different subjects of this, for example, and the model has roughly learned this predicate entailment relationship here. However, these models are kind of famously brittle, as I think a lot of the work on contrast sets and counterfactual examples has shown. In particular here, if you say 3 animals are running, the model will incorrectly judge entailment. We don't know if there's a third animal, right? So when the model's latent reasoning is flawed, it's hard to diagnose. I think another good example of this was all the work on multi-hop question answering a couple of years ago, which showed that a lot of the systems for this actually were doing just single hops of reasoning. And the only reason this was kind of news at all was because when all this reasoning is latent in a neural net, it's easy to look at a good performance number and assume that the right thing is happening, but that wasn't the case. Okay, so the question is, where does this break down? So we can keep trying to push these latent reasoning models with things like better data, methods for debiasing or handling spurious correlations, contrastive learning, but I think there's a point where it fails. Let's look at this example from the natural questions data set. What age do you need to be to buy a BB gun? And this is then on the right, the passage in Wikipedia that's annotated as the gold answer for this in the data set. So one thing you'll notice is that this only applies to Canada. It talks about what the age is in a bunch of Canadian provinces. So I'll give a quick plug here for some work that Michael and Unsula at UT have been doing on a new data set that captures these sort of extra linguistic contexts. Like if I'm asking this question in Canada, maybe this is the right answer. Okay, but I think the other thing going on here is that it talks about purchasing an airsoft gun, and we asked about a BB gun. Are these the same thing? It's actually a little bit complicated. I'll leave it to you to go Wikipedia that. And so there's two things I would say. The first is that end-to-end models don't model these nuances all that well. And the second, if I'm going to go try to buy a gun and break the law, I probably want some kind of justified reasoning in addition to just like the answer, like how old do I need to be? Okay, so when thinking about justified reasoning, let me kind of take a different tack, which is doing things with theorem provers. So the classical way of handling this kind of entailment example, going back to our example about the dog and the cat, would be to take these sentences, parse them into some kind of semantic representation, and then use some kind of a theorem prover to try to derive the entailment relationship here. So this is great. It has a lot of advantages. It articulates some really nice intermediate reasoning states. We're really good at doing search in these kind of theorem provers. People have been thinking about that for a long time. The drawback is that this requires a high coverage semantic formalism. You need to be able to parse into that formalism, and then you need all this background knowledge in the theorem prover that's really tough to learn from data. So here's the kind of vision that I'm going to sort of propose today, which is that we have a bunch of evidence. Let's say these are sentences from Wikipedia or kind of information, and we have some claim that we want to fact check or question we want to answer, some kind of information need. What we should do is form intermediate conclusions along the way and eventually be able to prove or disprove our claim or answer our question. And we should do this reasoning in natural language. So this is going to echo, again, some of the other invited talks we've heard this week, in particular Pete Clark's. But I think that what's really powerful about these kind of representations is that they combine both logical inference, the kind of things that theorem provers can do really well at, with lexical inference, capturing effects like paraphrasing. So the way I see it is that there's sort of a continuum here, where on the left we have theorem provers and frameworks like natural logic, which stipulates a way of doing reasoning in natural language, but it relies on things like WordNet and lexical relationships in order to derive relationships between pairs of sentences. And on the right here, we have latent reasoning approaches, or sort of ask GPT-3 to explain why this is the answer, which can do some really amazing things, but aren't necessarily grounded in a reasoning process. And so we're going to try to kind of get the best of both worlds with this work today. So why is natural language kind of useful here? So the first is that it's expressive. Text is a broad coverage semantic representation, I would argue. And if we look at this example from above, it's easy to represent the entailment and kind of break down what was going on in that reasoning process here. It's flexible. We could combine it with pre-trained models, information from Wikipedia, common sense knowledge bases, etc. And finally, it can give rise to these interpretable reasoning chains that we can look at, interact with, etc., which is much harder to do with things in formal semantic representations. So the catch is obviously that this is challenging to do. We need the right data, and we need to ensure that our models are doing sound reasoning. So most of this talk is going to revolve around what data sets you need and what are the frameworks for tackling these sorts of problems. So we're not going to get anywhere close to that grand vision, but I'm going to talk about two projects today which bite off little pieces of it. So first, I'm going to talk about some work on using textual entailment to verify QA systems, which involves some natural language manipulation that has to be logically consistent if we want to verify these things correctly. And second, I'm going to talk about some work on building a building block that can plug into this larger reasoning system, deriving intermediate conclusions. And this is a module we call natural language deduction. So let me start with the first piece here. This is work led by Jifan Chen, also joint with Unsel Choi, to appear at EMLP findings. Okay, so what do I mean when I say verifying reading comprehension? So imagine that we have a kind of great end-to-end latent reasoning QA model off the shelf. So we have a question like who plays the bad guy in the good place, and this model might do a retrieval step, or maybe it already knows what passage to look at, and you get some passage, and then you bash it all through a transformer, and you get an answer out. Okay, so the thing that we're trying to do here is check the answer. There's a few reasons you might want to do this. This might be able to help us with unanswerable questions. Maybe you get an answer and that answer is not quite good enough, but it's still the sort of best thing that the QA model can find. We can try to improve the confidence in our model. Like say, can we kind of construct the reason that this is the answer, and in doing so, make it so that our model can sort of say, I don't know, if it's not as confident. And you can also take this approach and do other things like validate presuppositions in the question, which is something that's been studied recently. Okay, so let me show you how we try to do this with NLI. So we take this candidate answer and our question, and we pass them through a question to statement converter. So this is a module that's been explored by Dembski et al. And in, of course, a lot of earlier work too. We take their approach of using seek-to-seek models, and we use a big pre-trained model. We use T5 3 billion to do this, trained on their data set. And so we can convert the question and answer into a declarative statement like this. So then we take the passage here and we pass it through a decontextualization model. So this is a module due to Unsel Choi and her collaborators at Google. And what they did was they figured out a way to take a sentence and then make it stand alone and be presentable as an isolated piece of evidence. So in this case, for example, we replace the series with the series The Good Place. So there's all kinds of anaphora resolution and rewriting of ellipsis and things like that that are going on here in order to make these sentences stand alone. All right, and now we have a premise and a hypothesis that we can feed into an NLI model, and the NLI model says, not entailed here. So in this case, the model was actually right, but for the wrong reasons. So the context, the premise here, did not sufficiently support the hypothesis, and so the NLI model rejected it. Okay, let me just kind of review that whole system real quick. So we have our QA system. It produces an answer candidate. We feed it into this verifier. That verifier uses these two pieces and this NLI model, and in the end produces a confidence score. So in reality, we get confidence scores out, which are just the entailment probability according to the MNLI model, or sorry, the NLI model. And then we take those confidence scores and we want to use them to do all this stuff that we talked about a couple slides ago, like rejecting unanswerable questions or low confidence answers. Okay, so the first experiment that we did here was starting with a system trained on Squad 1.1. So every question in Squad 1.1 has an answer. So we trained a system there, and then we ran it on Squad 2.0. So that data set contains unanswerable questions. So then we kind of find, in a sense, essentially the best answer that we can, that we can try to find there. And we want to use this verifier to reject the questions that are unanswerable. All right, so using our pipeline and then a Roberta MNLI model, we can get about 80% accuracy at both rejecting the unanswerable questions and accepting the answerable questions. So this obviously doesn't push the state of the art on Squad at all, but I think this is an interesting zero-shot result because the NLI model is not trained on Squad at all, and this pipeline's not optimized end-to-end. But we're able to take these off-the-shelf components, reformulate these kind of question answering examples, and use an existing MNLI model that was kind of formulated in and data was collected for in a totally different fashion, and actually do a pretty decent job at this problem. So I think this showcases the flexibility of these natural language representations. And the fact that we can use MNLI as a module off the shelf is just entirely due to the fact that we're able to do this kind of reshaping. And one thing I want to point out is that there's been some other work recently looking at formulating kind of document level NLI tasks or reformulating QA as NLI. But in a lot of that work, they take whole paragraphs or whole documents as the premises, which I think would be a great capability for NLI systems to have. But then there's not as many off the shelf models that are sort of usable for this. So you can't just plug those directly into MNLI like we can. All right. The kind of main experiments that we ran here were looking at a selective question answering setting. So we trained a model on the natural questions data set, and then we looked at natural questions and also 4 out-of-domain settings. And so these models often do pretty badly out of domain. So our question was, can we answer only a relatively small fraction of questions, but do so with high accuracy? So that's what this graph shows. The x-axis coverage here is the fraction of questions you're answering, and the y-axis is the answer F1 that you get. So this orange line here is what happens if you just take the QA model's posteriors as confidence values. So this is actually a pretty good baseline for a lot of calibration work. And you could see that already if you kind of ask the model to only answer 10% of the questions, it can get around 85 F1. This green line was our best system here. So this combines QA posteriors with a verifier that was trained on both MNLI and also a reformulated version of natural questions we call NQNLI. That was basically converted to NLI using our framework. So here, you're getting over 90 F1 at this kind of low coverage, and in general, it improves the kind of confidence estimates of the model. And I think there's actually a reason why this result is sort of even better than it appears, which I'll come back to in a second, because I want to talk about some of the errors these systems make. So the first thing I want to emphasize is that there actually aren't a lot of errors due to question the QA conversion or the decontextualization phases. Once you use these big models like T5 3 billion, this works pretty well. So we were using smaller models, and Jifan had just come back from an internship at Google. And so he had been drinking the T5 Kool-Aid and wanted to throw the big models at it. And that actually did make a difference here. So a lot of the errors that we see are, of course, just entailment errors. Like the model has a question answer pair and a premise, and it just makes the wrong judgment. But sometimes it disagrees with what's in the QA data set and is actually right. So here's an example of where that happens. So we don't have, unfortunately, a Thomas Edison example. I would have reworked it if I had known Daphna's example in advance. But here we have John von Neumann develop the central processing unit that's our kind of proposed answer. And here is the context that, again, is the gold annotated answer context. He talks about how he distributed the paper entitled First Draft a Report on the EDVAC, but it doesn't actually say anything about inventing the CPU. Now, whether he did or not, again, we're not going to get into that. There's lots of Googling you can do. But the NLI model kind of disagrees, and in my view, correctly says that this is not enough evidence to support that assertion. So I think what's really nice here is that we can explicitly examine the types of assumptions we're making in our models. Is this evidence actually sufficient to validate the answer here? We can now kind of see that laid out as opposed to just, here's a question, go find the right answer, here's the whole internet and here's the right answer, where we don't have as much of a sense of this kind of evidentiary burden that the model should meet. And I want to just close off this section by contrasting with the earlier approach that we tried for this problem. So this is from Jifan's earlier work at NACL, where we looked at forming graph structures with a combination of coreference and SRL to basically kind of draw in relations between predicates and arguments and build a coreference graph over the documents. And then we used a BERT model to basically treat the QA process as a graph alignment. So this model, I think I encourage you to check out this paper. I think there's a lot of cool things going on here. One thing I'll emphasize is that it can localize errors to particular parts of the input. So the reason we wanted to explore this was to see if, basically Super Bowl 50 aligning to Champ Bowl in this adversarially added sentence would allow us to basically more explicitly articulate where the model's going wrong. But this was much harder to parse into, and also it was less expressive than natural language. We found it a really hard time kind of imputing semantics into these graph alignments. And then if we tried to use more sophisticated semantic representations, things would just totally fall apart in terms of not being able to parse into them. So I think this kind of highlights the benefits of this sort of pure natural language approach to this kind of verification. We can take these existing modules that we have and do this manipulation in a pretty reliable way to do this decontextualization and conversion. And this allows us to employ NLI as a kind of off-the-shelf module for improving the performance of QA at these in these two different settings. And I think generally, as I said, this kind of paves the way for exploring more what NLI can do in terms of making these assumptions explicit and allowing us to explore both our model performance, but also our data sets. Okay, so that was the sort of first part I wanted to talk about. Now I'm going to dive into the second part, which is, again, about building this sort of deduction piece for trying to do this reasoning in long horizon natural language reasoning systems. This is work led by Kai Bostrom, also with Lucy Zhao and Swarat Chowdhury from UT. So what is natural language deduction? So we have two sentences here as inputs. Apples belong to the tree fruits and the produce of fruit trees can be eaten. And something that we can conclude from this is that apples are edible. So roughly what we want to do is take two, or in general, it could be one or more natural language statements and generate a valid conclusion, or place a distribution over the set of natural language strings that constitute valid conclusions from this from these inputs. Okay, so this is sort of, I would say, clearly in scope for a model like BART. The big question is the training data. So Pete Clark earlier this week gave a talk about their new work on this entailment bank data set, which I'll come back to in a little bit. That's a kind of supervised way of annotating data for this task. So I'll talk a little bit about that data set in a bit, but our approach that we took sort of in parallel with them was trying to tackle this in an automated way. So basically, can we automatically collect training data that shows these kind of deductions? And so we really need to have that training data exhibit two things. The first is that it needs to show us examples of logical inference. For example, fruits are edible, apples are a fruit, apples are edible. So it's like, things of type X have property Z, Y's are X, therefore Y's have property Z. So the fact that I was able to abstract that away from the natural language realization, I think shows that this is, kind of invariant with respect to lexical content, but these are also the kinds of things that are hard to write down. This is kind of the more theorem provery side of things. All right, and then we have lexical inferences, like something is edible means that it can be eaten. This is the kind of stuff that just wrecks theorem provers, because kind of unifying these two predicates, recognizing that they're the same, this is really hard with a lot of our existing semantic representations. But it's easy to do distributionally. So our approach is going to be based around automatically generating data that exhibits these logical inferences, then using a combination of pre-trained models and some paraphrased data augmentation to get at this lexical inference piece. So our pipeline, which I'll go through in a little bit of detail, looks like this. We take Wikipedia, we scrape it to find a bunch of sentences that exhibit the kinds of deductions we're looking for. We use some templates to transform those into examples of what we want, and then we use paraphrasing for data augmentation. So this first step, we employ a set of Hurst patterns that operate over dependency parsed Wikipedia to learn to find the kinds of examples we need. So this is a pattern for X such as Y can do Z, basically. So we find an example like this. The fertile basins, such as the large Thuringian Basin, are in intensive use for growing fruits and vegetables. All right, now for this particular Hurst pattern, we've written a template which rearranges this content as follows and does a little bit of a kind of reinflection as well, just to handle morphology. So we can rearrange that in a sort of cut and paste fashion to get the following. The fertile basins are in intensive use for growing fruits and vegetables. The large Thuringian Basin is a fertile basin. This is the kind of inference that the Hurst pattern supports. And then that yields as a conclusion, the large Thuringian Basin is in intensive use for growing fruits and vegetables. All right, cool. So we've got an example of a deductive inference here, but if you train a model on this, it's just going to learn to copy and rearrange stuff in pretty trivial ways. So here's where the paraphrasing comes in. So we run a paraphrasing model on the premise statements here from our automatically scraped deduction example. And here's what we get. Growing fruits and vegetables requires a lot of fertile basins. The Thuringian Basin is fertile. Okay, so the second one of these is good. The first one is fairly questionable, but it's kind of, data augmentation, right? So it doesn't need to be perfect. And what we find is that it's kind of decent more often than not. And even though the model sees some noise, the targets here are all sort of valid conclusions. And so the model generally learns to do sound reasoning here. So this is our whole pipeline, and it doesn't find actually very many examples of this type of reasoning in the grand scheme of things. We only get about 40,000 sentences from scraping all of Wikipedia. That's okay. I mean, that leads to a final data set once we do this paraphrasing of about 100K examples, which is enough to train our models. Okay, so here's the kinds of things we can learn to do. So doctors use medical tests to diagnose diseases and guide treatment. Some of the most common diagnostic procedures include blood counts and other multi-factor panels. So one of our baselines was just training a BART model on MNLI to generate the hypothesis given the premise. And this just repeats the first premise that we give it. Our pattern-only model that doesn't use paraphrasing also just repeats the first premise. But our full model is able to do this unification over diagnose and diagnostic procedures and kind of produce the correct inference here. Doctors use blood counts and other multifactorial panels to do this stuff. And here's another example from the entailment bank data set. Humans changing an ecosystem has a negative impact, blah, blah, blah. Humans building homes causes an ecosystem to change. We recognize that causes X is the same as X, and our model is able to make this inference. So we looked at two data sets. The first was the question answering by sentence composition data set from Tushar-Kott et al. And this data set basically has pairs of evidence sentences that combine to form a conclusion. So we tried a zero-shot version of GPT-2. This basically doesn't work at all. We've tried this with GPT-3 and seen some kind of interesting stuff, but maybe I'll leave that for the question period or the discussion. And a lot of the other, the kind of MNLI BART doesn't really work at all. And the interesting thing is that our model is basically able to match the performance of these in-domain supervised BART models, despite using synthetic supervision. And what I think is really cool is that when our model is wrong, a lot of times what it does is repeat stuff. which in the context of a bigger reasoning system is like not the worst failure mode, right? Because it at least is being correct. It's just not saying anything new or useful. So these were all rated by basically looking at the, looking manually at the conclusions. We also have some results on perplexity and blurt in the paper, but evaluating this stuff automatically is really hard. And so here's what happens on entailment bank. So we see a similar trend where modulo grammaticality, we can actually do basically as well as their model on these substitution patterns, with the caveat that if we look at all their examples, there's a number of patterns that we kind of still can't handle. But our approach is scalable, and so we think that we can bridge this gap, and we're kind of looking at that in ongoing work. Okay, so the takeaways from this part were that we were able to, with little human intervention, get a model that can do this kind of broad domain reasoning and capture these patterns. So these are very expressive models and also flexible. We were able to take these existing data sets, including one that was released basically in the final stages of the project, entailment banks also appearing in EMNLP, and run the model on them without much modification. And finally, we were able to kind of use this approach of paraphrasing to sort of teach a pre-trained model to do these kind of lexical inferences. And so that's the kind of capability that I think is maybe most exciting out of all of this. All right, so that's what I wanted to mostly cover today. Let me just kind of conclude by showing a few, I think, of the future directions that we hope that this stuff can, basically hope where we can see some progress. So let me come back to this, this overall vision, which I think is one that's actually shared by quite a number of folks, including, like I mentioned, Pete Clark's talk earlier this week touched on these sorts of ideas as well. And so what I would really hope to see is that we could get a broad set of operations like deduction, decontextualization, summarization, sentence compression, simplification, all kinds of things, and that these can all kind of work together to yield the conclusions that we need. Now, one thing that we still need is how to do planning in these spaces, right? We've got all these operations. Our state space is kind of sigma star if you think about all the things that you can say. And, doing search in that is tough. So there's been some very recent work from Arab Shahi et al. With the clue system that has a very cool backward chaining approach to doing reasoning and common sense knowledge bases. So I think we're likely to see more kind of progress in that front as these individual pieces get better. And in terms of goals, I think that one problem that I've gotten sort of interested in is fact checking. So a lot of times when you have claims that are made by politicians, like things on PolitiFact, you have these complex claims that have multiple pieces. So Angela Fan et al. Have this very nice data set called Generating Fact-Checking Briefs from last EMNLP, where they look at breaking down these claims into a kind of different questions and then retrieving evidence for each part of the question. So they evaluated in this very human-centric fashion, but I think that kind of with enough progress here, we could also kind of throw it into this automated system. And then finally, just to kind of plug one more new data set. So this is work by my student Yasumasa, joint with Michael and Unsel, about reasoning about entities. So this was also inspired by the strategy QA data set by Morkeva et al. And the idea is to have claims which involve both kind of knowledge about an entity, so kind of something from Wikipedia, and also some kind of common sense. So Harry Potter can teach classes on how to fly on a broomstick. So we don't, unlike strategy QA, we don't have explicit strategies for these things, but I think it would be great if we can eventually kind of get to a world where these sorts of textual reasoning techniques can articulate and materialize explanations for this stuff. Okay, so I'll leave off there. And complex reasoning, I think there's lots of opportunities now for natural language to kind of do cool stuff there. Natural language is expressive, flexible, and interpretable. And I think as we're starting to see more progress in big pre-trained models, few-shot learning, new data sets, we're starting to see this become really a lot more viable, even over the last year or so. And so I'm really excited about where the progress on this can lead. So that's all for me for today. I'm happy to stick around and take questions, and I'll be in the discussion. And I want to thank my collaborators on this work and all the other work from my lab, as well as my funding sources. Thank you.
Thank you, Greg. This is a very interesting talk. So we still have time for a couple of questions. Yeah, you can also read the question from the screen, but yeah, let's take a few questions. So the first question is, in general, question answering seems to be a cleaner, more precise task, while natural language inference seems to one that is actually more ambiguous. Does it make sense to verify an easier task using a more challenging task?
That's actually a really I really like this question actually. So I agree that NLI is ambiguous. Like there have been all these recent papers, like the chaos NLI data set from UNC folks, I think, and then also Ellie Pavlik and Tom Kwiatkowski's work on kind of human judgments and this stuff. And I think when you're looking at sort of encyclopedic question answering, I think that there are gray areas, and I think this is where reasoning and explanations can really help us articulate them. So maybe there's some logical leap you need to make, like an airsoft gun is a BB, an airsoft gun and a BB gun. Like does one of these terms kind of entail the other, right? So I think it would be great to be able to say, yes, it's entailed modulo this assumption that I don't know how to check. So that would I think be a great thing for a QA system to output. And I think NLI is a more natural way to articulate those kind of assumptions. So, I mean, again, QA and NLI are in some sense just reformulations of the same thing. And QA is so broad that, I think it depends on which data set you're talking about, whether it's actually cleaner or more precise. But that's how I kind of see them interacting.
Great, thanks. Okay, so the next question, actually, I believe that you addressed this question, but yeah. So the question is, so you mentioned several components in your pipeline model, including the question to statement conversion, the decontextualization model. Are they so good so that we don't need to worry about error propagation?
Yeah, I think I would say no. Like, I think you should always be worried about error propagation. But what we found was that they were definitely not the bottleneck for us. And that was slightly surprising to me. And I do think that, like, I think in the sense that, like, we view like part of speech tagging as sort of solved, and that you'll run the tagger and you won't really worry all that much about, like, do I need to open up the tagger and kind of look at the errors? Like SRL is definitely not at that point. And I would say something like the question to declarative statement conversion was starting to feel more at that point at the end, where when we were getting errors from it, it's because the question was so malformed and so mangled that, like, we couldn't even often figure out what was really being asked. So, yeah, so I think you should always be worried about it. But yeah, not a lot of our errors were due to that stuff.
Great, yeah, thanks. Okay, so the next question is, did you try logical inferences with negations or even softer statements such as most or some? How well do you think your models can perform?
Yeah, I'm not quite sure actually which part of the talk this was asking about. I think I think NLI, these are sort of bread and butter for NLI. But we didn't sort of see it as much there. I think in the deduction piece, most or some, I mean, like, obviously there's sort of a level where kind of handling quantification and handling soft reasoning is something that is just very challenging to represent. So we didn't look at this a ton. I will say that we did a little bit of work looking at kind of inference with quantifiers, and just sort of bailed out of it and focused on the pieces that we focused on. But it's absolutely something that we want to come back to with that.
Great. Okay, so the next question, given the premises is a distribution of the conclusion well defined, any premise can also be a valid conclusion. What does it mean to assign probabilities to different conclusions?
Yeah, this is a great question. So, I mean, I think, so I think there's an implicit notion in this that, we didn't really get into in that work. But, like, when you want to plug these things into a larger reasoning system, there's a notion of kind of the goal, right? If you're doing search, you want to get close to, let's say, generating conclusions that are useful for fact checking the thing you're trying to fact check or whatever. And so I think I think you're right that there is a very flat distribution over, like, things that are true, right? Any proposition expressed in the premises, you could just repeat, right? But I think there's a much smaller set of things that kind of meaningfully unify the two premises in a way that humans would like, in a way that also gets us closer to the goal. And so, I mean, I think, like, effectively that's what we're learning models to do, not really, like, kind of modeling any valid conclusion. And yeah, and so I think there's I was talking with Ray Mooney about this, and there's like a term for this in Prolog search, and I'm blanking on the term now, but yeah, so I think the idea of the kind of goal conditioned generation of these deductions is a sort of important piece here that I kind of glossed over.
Okay, yeah. Okay, let me take maybe 2 more questions. So the next question is, are there cases of question answering the correct, but the entailment gets it wrong? Any intuition why the entailment probably easier than question?
Yeah, we actually get a fair number of these examples where, you know, I would say it's sort of possible. I don't have any good example off the top of my head. I would say that there are a number of cases where like it's you can infer it, but when you look at it and kind of compare it to NLI, you're like, oh yeah, like of course the model, you know, of course the model didn't quite realize that like, you know, yeah, and that I'd have to pull up the Google sheet of all our error analysis, but these definitely happen. And I don't think it's strictly easier. I think in many ways, entailment, at least when you compare it against natural questions, is a stricter, is a kind of stricter criterion. With regard to ensembling, we did try a you know, we did try a, you know, basically explicitly stapling 2 QA systems together to try to control for ensembling effects a little bit. What I would say is that the, you know, it is ensembling in the sense that like when transferring to out of domain, MNLI sort of teaches useful additional inferences and kind of gives you a level of inferential certitude that is not that easy to obtain just from the one in domain data set. So like, yeah, I mean, it is because we're able to then staple in and use extra data, not just because of the reformulation of the problem.
Sure, yeah. Actually, I think the next 2 questions are pretty similar. Maybe I'll just take the last one. So if my understanding is correct, the NLI model was trained on MNLI. How many errors actually come from the domain transfer compared to like training an NLI model on Wikipedia?
Yeah. So this, again, I kind of glossed over. We also explored basically taking natural questions and using our whole pipeline to turn natural questions into an NLI data set. And most of the work that actually was done here was like figuring out how to staple these 2 things together, you know, in a nice way. So I think that because we're also looking primarily at calibration in out of domain settings, which I think is the kind of more interesting place and the place where we have a stronger lever here. Because that's what we're looking at, the errors that can arise, I think, like a lot of times the sort of out of domainness of the NLI is actually a virtue because it avoids you overfitting to the Wikipedia domain when you're kind of transferring and running the model somewhere else.
Great, thanks. Yeah, maybe we should just wrap up here. And Greg is going to stay for another 30 minutes on gather time. So if you have any questions, please just ask him here. Okay, so next I'm going to thanks Greg for coming and thanks for the great talk.
Thanks so much.
So next I'm going to hand this to Samir for a very short closing session. Yeah.
Cool. Hey, thanks, Tanji. Give me a second as I share my screen. All right, thanks, Tanji. All right, so thank you everyone for being here. This was the 3rd AKBC, and I think it went off really, really well. Even though these are closing remarks, I would like to remind everyone that this is not actually the end of the conference. We have 2 days of exciting workshops. I'm actually really looking forward to these. Tomorrow we have 3 workshops on conversational agents, on argumentation, and on how to combine structured and unstructured KPs. And then we have a 2nd day of workshops on the 8th, including common sense reasoning, personal knowledge graphs, natural language on scientific texts, and how to do explainable graph-based machine learning. So yeah, I encourage all of you to go and attend all of these cool workshops. Now, I'd also like to thank a few people that sort of made this AKBC possible. At the most important, I think, was the organizing committee. You know, I had Andrew, Danchi, Jonathan, Matt, Ansel, and Walid all sort of coming together and making this conference successful. One thing I'll point out is when you're working with a bunch of people about working on a conference, you kind of want them to care as much about it. So you want them to be at least as stressed as you are, maybe a little bit more stressed. And I will say that this committee definitely met that criteria. So it was really nice to know that everybody was on top of things. I especially want to thank student volunteers. These are ones that have been mostly in the background. Most of you probably didn't even realize that these guys were working really, really hard. The website was regularly updated and initially built by Moir. Anthony Chen, who was working on the virtual site and the registrations. Every time you got those emails, that was transparently done by Anthony. And the social media side of things, Howard has been really on top of it, sending out the tweets, letting everybody know what's going on with the conference. So really want to thank all of these folks. I also want to thank all of the area chairs that made sort of the reviewing and selection of good papers possible. It's been really exciting to see the program that we've been able to put together. In the end, I also want to thank Janet from UCI, who was sort of working on the budgetary side of things, the open review team that was, we were able to carry out the reviews, and all the reviews are available. If you have questions for the authors, if you want to discuss more, you can use open review outside of just the review system. And I also want to thank Allen Institute for AI for hosting this website where we are doing this virtual stuff. Okay. So now the question is, what's going to happen next year? And in order to do so, I'm going to invite Sebastian to say a few words. So here he is.
It's my great pleasure to invite you all to London or Zoom next year to attend AKBC 2022. I don't think I need to convince you that London is a great place to visit. It is objectively the best city in the world. And that's not just me who says that. There's also a random website online that happens to say exactly the same thing. But on the other hand, is not quite agreeing. But I think maybe this tells us just that language models are not knowledge bases yet. That said, we all know that it's critical how to prompt and query these models. So asked the right way, I think Bert does know the correct answer too. But seriously, London is amazing, and it has so much for you to see. World-famous sites like the London Eye, the Tower Bridge, the Big Ben, and Buckingham Palace, just to name a few. Amazing free museums like the British Museum or the Natural History Museum, as well as world-leading universities and amazing food and food markets such as the Borough Market. Maybe most importantly, as you can see on the photos, and really regardless of the season, London just has also the best weather. So I really hope to see you there.
All right. Thanks, Sebastian, for that. So yeah, see everyone next year at London, hopefully in person. We're still trying to figure out what the format would look like. But yeah, that's pretty excited about that. So in the last thing I want to say is we really, really appreciate all of your feedback. So that's the email address. Please send us any comments that you have, what you think about the sort of conference date and deadlines, what is the ideal meeting format, especially as we transition hopefully to an in-person meeting. How much would you like the hybrid part of these things to be the core part of conference? What do you think of the reviewing? Are there communities that we should be reaching out to that we haven't yet? And if you have anything else, we might even create a survey and send out something to that effect. But if you have views already, please email us. So with that, I am going to, so now the next thing is essentially the chats and the spotlight. The chats and the poster session. So I encourage everyone to go and check those out. Here is the actual schedule. All right, thank you, everyone.